Okay, it seems we are live now. Uh, so I think let's start the afternoon session. So welcome everyone, and so the first talk in the afternoon session will be given by Professor Vasudev Dasgupta from Department of Theoretical Physics at Tata Institute of Fundamental Research, TIFR, Mumbai. And Professor Dasgupta is a leading expert, I would say, in the field of astroparticle physics. So his research interest lies in the interface of particle physics, astrophysics, cosmology, and especially in the field of neutrino physics and dark matter. Professor Dasgupta did his PhD at TIFR, and then he went abroad for postdoctoral studies, first at Max Planck Institute in Munich, and then Ohio State University in USA, and then ICTP in Italy. And in 2014, he joined TIFR as a regular faculty member, and since then he's there and working actively in the field of, as I said, neutrino physics and dark matter. And 2019, if I am correct, ICTP, the one of the prestigious institute, has given Professor Dasgupta the ICTP Prize Award. And I'm quoting what they said for his contribution, innovative theoretical contributions to neutrino physics and dark matter physics. So I must say thank you to Professor Dasgupta for accepting our invitation. So stage is now yours. So we are very happy to have you here and to listen to you some of the interesting research topics, especially in the field of dark matter physics. So yeah, you can start now, Professor Dasgupta.
Okay. Am I audible?
Yes.
All right. So thank you, Amit. Thank you, Professor Thapa. Thank you to all the organizers of this symposium. It's a pleasure to speak to all of you. I'll tell you a little bit about dark matter. So let me start by sharing my screen. I hope all of you can now see my slides.
Yeah, it's visible.
All right, so let's get started. I want to tell you a little bit about dark matter today. So there's this evocative title, The Mystery of Invisible Mass. And indeed, invisible mass is a better name than dark matter, and you will see why. That is, in fact, the main point of the talk. That what is dark matter? Dark matter is just invisible mass. So it's nothing mysterious. It's just mass that we cannot see. So this is a picture that all of us are very familiar with, I hope. You can all recognize yourselves on this picture. Somewhere you are a little tiny dot on this picture. And the yellow dots in this picture trace human populations, whereas the dark, empty spaces are regions where no human beings live. So when one sees this picture, one does not think that the dark areas are empty, that there is some vacuum there. No one sensible ever imagines that just because there is this dark black region to the south of the Indian southern peninsula, that there is nothing there. No one thinks like that. And the reason is that we are very familiar with our surroundings. During the daytime, if we go to the seashore, which I'm very lucky to be able to do here at TIFR every day, we see that what I see here as this dark black region is nothing but the Arabian Sea or the Bay of Bengal. So we know what's out there. And the reason is that while we can't see it in this picture, in our day-to-day lives, because of light that arrives from the sun, gets reflected off these objects, the oceans and the seas, and then comes back to our eyes, we know what these objects are. So our intuition is intact. We know what these dark regions are. We are not confused. But consider this picture. Now, this is also a familiar picture, perhaps not quite as picturesque always, but well, some of us have seen night skies almost as beautiful as this. And when you look at this picture and you ask, okay, what do you see? You can see the arm of the Milky Way, which is around here. And then if you go deeper in that picture, that's what I have tried to simulate. There are lots of bright dots. Most of these are galaxies. And if you have a sufficiently powerful telescope, you can see some of these galaxies in their full glory, like the one that is being shown here using this artist's composite. So both of these pictures are real pictures taken using the Hubble Space Telescope. So this picture of this galaxy in the center and the background galaxies, they're both real photographs taken with the Hubble Space Telescope, but they're not seen on top of each other like this. What I have done is I've just simply superimposed a big galaxy on a background of galaxies, to kind of give you the impression of what it would look like if you saw a big galaxy against a background of smaller galaxies. But still, you see, even when you use the world's best telescopes, there are regions of the sky, the regions of space, that appear dark. So, for example, this region where I am showing you using my pointer now, or perhaps, let's say, this region. Okay, so these are voids. There's a big void over here, you can see. And no stars, no galaxies, nothing over there. So I could ask that, okay, what is there in that region? Is that empty? And at this point, most people would start at least becoming a little bit less confident in their answer. They would say that, no, okay, if you have used the world's best telescope, the Hubble telescope, and still you don't see any stars or galaxies there, maybe they are empty. And often they are right, but not quite. If you go further, if you take a more zoomed out picture of the universe, now we are not looking at a small part of the sky. We are looking at a part of the sky that is 100 million light years across. And this is not a real picture. This is not taken from some telescope. Rather, this is a computer simulation of what our universe looks like on this size. It's called the Aquarius Simulation. So these use supercomputers to make these simulations. These yellow dots are our galaxies, all the galaxies which have stars in them and so on. And you can see that they form these networks and filaments, that kind of join up with each other and form what is known as the cosmic web. However, I hope you can also see that these galaxies are embedded in a hazy fog that's colored gray here. And then there are regions that are truly dark, somewhere in between here. Okay, I hope you can see this, that these visible galaxies are embedded in this hazy cloud, which is not colored yellow, that has been colored, false colored in this bluish gray color. And that's because this is a false, simulated picture. So we can color them as we like. This gray stuff is what dark matter would look like if we could see it. All our galaxies, stars, everything that we see, they are embedded in this vast diffuse network of dark matter structure that permeates our entire universe. If you focus deeply on one galaxy, again, this is a artist's composition of some galaxy like this. It's approximately 100,000 light years across, but it sits in a dark matter halo, which is approximately 10 times larger. Okay? So the picture that you need to have in mind, what is dark matter? Dark matter is this stuff that exists around our galaxies, forming this vast diffuse network, and it has mass. This stuff which is colored, this hazy gray blue, halo on the outside of this galaxy, it has mass, and that's how we know that it's there. That's what I'll talk to you about. But this is the mental picture that you first need to have. That what is dark matter? Dark matter is some hazy, fuzzy stuff that surrounds our galaxies. Okay, and there's a lot of it even at the center of our galaxy. But the most important thing is that it extends way beyond the galaxy. Okay, so now we can start our actual discussion. There are two questions that I want to answer. The first is, how do we know that there is such a thing called dark matter? So far, all that I have told you is, this is what it should look like. This is what, but then I have not argued logically why you should believe me. I could be telling you a lie. So why should you believe what I am saying? So that's the first question. How do you know scientifically that there is such a thing called dark matter? That's the first question. And this is a question that I will be able to answer, hopefully to your satisfaction, because the current scientific knowledge and consensus almost unequivocally tells us that there is such a thing called dark matter. Then that brings us to the next question. Okay, there is this hazy stuff around our galaxies. What is it? This is a much harder question, and we do not know the answer to this question. And I will not be able to tell you the answer to this question as a result. So instead of that, I will tell you how we are trying to find out what this is. And that's the field of research on dark matter, to figure out the nature of this dark matter that surrounds us. So these are the two questions. How do we know that there is dark matter? And what is it? Or how can we find out what is it? Okay. So the first mantra that you have to now remember is that all evidence for dark matter comes from this one very simple basic idea. That is that the motion of particles is affected by mass around it. So motion of some particle can measure mass. So the simplest example of this is very familiar to us. So imagine Isaac Newton standing on, in his garden with an apple in his hand. And what is the force that's acting on this apple due to the earth? It is G, which is the Newton's constant, times the mass of the earth, times the mass of the apple, divided by the distance between the center of the apple and the center of the earth, squared. So gmm by r squared. That's the gravitational force acting downwards on this apple. But we know from Newton's second law that this same force can be written as mass of the apple times the acceleration of the apple. Okay, and you can see that the mass of the apple, which is the small m, can cancel out, and I know what the acceleration is. And this acceleration depends on this large M, capital M, that depends on the mass of the Earth. Okay, so what I can do is I can rearrange this equation a little bit, and I can do a little experiment. I can measure the acceleration by just simply dropping this apple, and I know that the time it takes for an apple to drop, if it is t, and the height is h, then this height and this t are related using this simple formula which we learned in school. So in this formula for mass, this is just a rearrangement of the F equal to ma equation that we just saw. Mass is r squared by gravitation constant times the acceleration. And the acceleration is simply twice the height divided by t squared from this formula. So if you know the radius of the Earth, and if you know the Newton's constant, which you can measure in the lab, you can measure Newton's constant in the lab by just measuring force between two, small brass balls or whatever. The radius of the Earth can be figured out. For example, you could do triangulation. You could see how far ships have to travel in the sea before you lose them on the horizon. And from that, you can know the curvature of the Earth and therefore the radius of the Earth. So there are ways of measuring both capital R and capital G. Small h and t can be experimentally measured. You can measure how high the apple was before it dropped and how long it took it to fall. You have a stopwatch. So just by making these measurements, you can measure the mass of the Earth, and you plug in the correct numbers. R is some 6,000 kilometers. G is this Newton's constant that we know. Let's say the height was a meter, and you would see that it would take about half a second for this apple to fall, and you would determine that the mass of the Earth was something like 10 to the 24 kilograms. So this is a very simple example that shows that just by measuring the motion of this apple, I was able to measure the mass of the Earth. Quite spectacular, no? Very simple stuff. But this is the kind of stuff that we can use now in astrophysics to determine masses of various astrophysical objects. So let's do that. The first thing we can do is we realize that the average kinetic energy of stars in a galaxy or galaxies in a galaxy cluster. A galaxy cluster is a bunch of about 1,000 galaxies, as if it's like a cloud of galaxies. And all of these dots that you see, these are different galaxies. The different colors are the different speeds at which these galaxies are traveling. So if you measure the average kinetic energy of these galaxies and equate that with the potential energy, at that location, just by using this equation, again, you can compute the mass of this galaxy cluster. And it's given in terms of the size of this cluster of galaxies, the root mean square average of the speeds, and the Newton constant. Exactly like what we did in the case of the apple falling to the Earth. It's a very simple calculation. You do this and you find the mass. Turns out that the mass that you calculate by doing this observation is much, much larger than the mass that you can see. If you take each of these galaxies and add their masses, the mass that you get, visible mass in the galaxies, turns out to be much smaller than the mass that you infer by applying known laws of gravitational force. And these kind of arguments based on very basic physics. So there is some mismatch. So this was the first indication that there was some mass that was there in this astrophysical object. You couldn't see it, but you could infer it in some indirect way. And in fact, in this early study, it was found that the inferred mass was 400 times larger than the mass that was visible. And Fritz Zwicky called this invisible mass Dunkelmaterei, which is German for dark matter. Okay? That's the first line of evidence for dark matter. The next line of evidence is something that's also familiar to us. We know that satellites orbit around their parent force center. So the Earth goes around the sun, the moon goes around the Earth, and so on. And the speed at which they go around depends on the mass of the force center. Whatever is causing the gravitational force that leads to these orbits. So it turns out that you can show that the speed of the orbit, the orbital velocity, orbital speed of the particle that's orbiting some big mass of, let's say, mass capital M, it decreases as a distance away from it, and it decreases as 1 over square root of r. And here is a demonstration, this fact. On the bottom horizontal axis, you are seeing the distance from the center of our solar system, so from the center of the sun, okay, in astronomical units. So astronomical unit is the distance between Earth and sun. And on the y-axis is the orbital speed in kilometers per second. So here is Mercury, then Venus, and then Earth. Okay, Earth is at exactly 1 astronomical unit. Then Mars, Jupiter, Saturn, Uranus, Neptune. A few other objects like the Ceres, the Pluto, and Eris. These are small objects, planets. They are also shown. And you can see that their orbital velocities all very neatly obey this 1 over square root law. It's called the Kepler's law, as a function of radius. And this dashed line is this theoretical prediction, if you will. So you expect then that in a galaxy, which is a spiral galaxy that is rotating, stars which are further away from the center should also rotate at smaller velocities, and in fact it should fall off as 1 over square root r. This is the natural expectation. So this is what is shown here. So on the left hand side, these are both simulations, both not real data. On the left hand side is shown this spiral galaxy, which you are seeing face on. And on the right hand side, the same spiral galaxy, both again simulated. On the left hand side is shown what would happen if it obeyed this Kepler's 1 over square root r law. And on the right hand side is shown what is actually seen. So let's look at the video. If you notice, on the left, the edges of the galaxy are not rotating at all, almost, right? And the centers are rotating almost at the same level for both the pictures. However, on the right, if you notice, on the right, the edges of the galaxy are also traveling at roughly the same speed as the center of the galaxy. Okay. So this is different from the 1 over square root r, which is the Keplerian prediction. And it is also different from a rigid body rotation. No, in the case of a rigid body rotation, if the galaxy was like a rigid object and rotating with a constant angular momentum, then the edges would rotate much faster than the center, because V goes as omega times R, and R is larger at the edge. So the edges would rotate faster, but that's not what is seen either. Edges do not rotate as slow as Kepler would have predicted, and they don't rotate as fast as rigid body rotation would predict. It's somewhere in the middle. In fact, for many of these galaxies, spiral galaxies, what is called the rotation curve, so the rotation velocity as a function of distance from the center of the galaxy, it's almost flat. So this is a second line of evidence that something is wrong, and the understanding of this is simply that if there was more mass as you went outwards from the galaxy, and this mass was not visible, but acting on the stars gravitationally, then of course they would speed up a bit. And the amount of mass and the density of this uh, invisible mass is such that it precisely leads to these flat rotation curves. So now the second line of evidence is not only telling us that there is invisible mass, but rather that it is distributed away from the center of the galaxy in a specific way so that the rotation curves are flat. In fact, what you see on the top of your screen here is this is the M31 galaxy, the Andromeda galaxy, and superimposed on it is a distance scale in arc minutes. And this curve that you see with these dots and the error bars, these are measurements of orbital velocity. And you can see that although the galaxy ends roughly here, the rotation curves extends all the way out, at least a factor of 2 beyond the visible edge of the galaxy. And so you can then infer that there is mass beyond the visible galaxy, and it is distributed in a particular way. So this was done primarily by Vera Rubin and her advisor Kent Ford, and this was the second line of evidence for that. Then there is the famous idea due to Einstein that mass can bend light. We know that black holes, for example, can bend light around them. This is particularly well known to us because of movies like Interstellar. So this is used to measure also the masses of objects between some distant light source, let's say a quasar or a galaxy, and us. And this allows us to measure the masses of these intervening objects, in this case, a galaxy cluster. And from that, you can measure the mass. And again, you can compare with the mass that you see, and you find that the inferred mass exceeds the observed mass. That's the third line of evidence. In fact, this is a synthesized picture of what these lensed images look like. The yellow dots and blobs are background stars or galaxies. And the fact that they appear stretched in arcs, more or less around this center, is because there is mass. There's a lot of mass here, which has very helpfully been colored in this gray, hazy fog. So here you can see the dark matter because it has been helpfully colored, false colored for us. But even if it wasn't, just from seeing these streaks, these stars or galaxies that have been stretched into these streaks, by noticing that, we could have inferred that there was invisible mass in this region. Okay. So now we switch gears, and instead of just thinking about dark matter in galaxies or galaxy clusters, Now we come to the real evidence for dark matter, the really compelling evidence for dark matter. That comes from the observations of the cosmos, of the entire universe on the largest scale. The idea is very simple. The universe was very hot and dense in the beginning, and it was expanding. As it was expanding, it became colder. So in the early universe, when the universe was very hot, it was so hot that everything was ionized. So hydrogen atoms were broken apart into protons and electrons, and everything was, banging against each other. It's a plasma. And in this plasma, light cannot travel freely. So light would scatter of these charged particles, and it cannot reach us from that region, which is ionized. So as we are looking further back, at some very far away region of the universe, light that we see from that region was emitted long ago. And if we are seeing sufficiently far enough, this region would be giving us light that is very, very old, so old that the universe was perhaps not even transparent at the time. And so there is a limit to how far we can see. Because if we try to see too far, we are looking at a universe that is too young, or in our anthropocentric frame, too old, so very early universe, when it was not transparent. So there is this last scattering surface. So there is a surface, there's a screen, roughly speaking, beyond which the universe appears non-transparent. No, it's not transparent, it's opaque. And we only see the universe up to that last surface. It's like, imagine that you look up at the sky and you can't look beyond the cloud, because behind the cloud, although there is light, it can't reach you. Now, that's fine. So this is what any satellite would look at. This is a little patch of the sky. Now, it turns out that the light that arrives at us from this surface has almost, if uniform nature across the entire sky. In all directions, this photons that come to us from this surface, they have roughly the same temperature. However, there are small fluctuations, spatial fluctuations of the temperature. And these small spatial fluctuations of the temperature on this last scattering surface, they reveal us information about the early universe. So these fluctuations are called the cosmic microwave background anisotropies. Why are there these anisotropies? The reason is very simple. Imagine you have a pond, or a big pool of water. If you put your finger, push a little bit on the surface of this pool of water, you can push out some of the liquid because of this force that you have applied, but the water will go away a little bit, but then eventually it will come back, and then it will, make these waves even after you've lifted your finger away. The same thing happens in the early universe. There is some density of this plasma in the early universe. And by whatever accident, if there is some region of the universe that has a little bit excess matter, then it has more gravitational force attracting it, and so it tries to collapse. But as it tries to collapse, it becomes hot locally and radiation will push it out. Then again, it will push out too much. And at that point, the gravitational force will again take over and it will compactify again. And then again, the temperature would rise and again it would push out and it sets up these oscillations. These oscillations lead to waves in this primordial plasma. The nature of these waves, at what speed they travel, how much they travel, what is the size of the amplitude of these oscillations, all of these things encode information about the nature of dark matter and other things as well. But here we are interested in dark matter. In particular, so this is a bit technical, and if there's a question at the end, I will go into more detail. But here I will just state the fact. The height of the third peak in CMB and the slope of this large multipole moment part of this anisotropy power spectrum reveal information about dark matter. So this is a little bit technical, but if you want to know more, you can either ask me a question at the end. And if you are happy with just a simple explanation, it is that the nature of these oscillations of the primordial plasma, they contain information about dark matter. So from that, we know that there is dark matter. In particular, this is a demonstration. What is being shown in the pink bar graph, which is changing, is that we are dialing in different amounts of dark matter from, let's say, 10% of the universe to 50% of the universe, let's say. And on the in the yellow line, you're seeing basically the same curve that you saw in this plot here before. So if you want to have the second and the third peak to be roughly equal, which is what is seen in real life, you have to make this amount of dark matter roughly of the order of 10%, so 0.1. That's when these two peaks are roughly equal. And that's the way we know how much dark matter exists in the universe. That's one of the ways. Okay. So we've told you 4 ways of looking for dark matter, and here's the last one. We already gave you sort of a glimpse of what the cosmic net looked like. That was the simulation, the computer simulation of what the cosmic web looks like. Here is an actual map. So each colored dot in this picture is a galaxy that has been imaged by the Sloan Digital Sky Survey. The black cut-out wedges that you see are regions of the sky that they could not look at because, for example, the galaxy, our own galaxy, was in the way. So you have to look away from the galaxy. Wherever they could look, they found this very nice filamentary structure of the universe. And the nature of this filamentary structure, again, just like the nature of the waves, encode information about dark matter. In particular, one of the things that it says, because there are lots of very fine filaments here, it tells you that dark matter does not travel very large distances. If it could, then everything would get smeared out. So dark matter tends to stay in one place. It clusters. So this is a crucial piece of information that comes out of looking at the large scale structure, or colloquially called the cosmic net. So these are the 5 lines of evidence, the major lines of evidence for dark matter. And these different lines of evidence, whether it is rotation curves, dispersion velocities of galaxy clusters, lensing, large scale structure, cosmic microwave background, all of these things, they span a very wide array of astrophysical objects, from the Milky Way halo, dwarf galaxies, galaxy clusters, the entire universe, and distances all the way from 100 kiloparsecs to approximately a gigaparsec, so 1 billion light years or so. So we have a lot of evidence, very different lines of evidence using very different techniques, very different locations, all pointing to the same fact that there is invisible mass in the universe. We know how it is distributed in various galaxies. We know how it is distributed in the universe, in these cosmic filaments, and we know certain properties of it. Okay, so that's dark matter. But I want to make one more point before we switch to the second part of the talk, and that has to do something with dark energy. Now, although everyone is, perhaps familiar with this E equal to mc square, so matter and energy are very easily confused. Dark energy does not refer to anything to do with dark matter. Dark energy is a totally different thing. It says that the universe is expanding at a rate that is increasing with time. So it is usually shown like this. So here are some galaxies. Now, seen from, let's say, the bottom left galaxy here, which is, let's say, where we live, the other galaxies appear red because they're receding away from us. So if I were to superimpose one picture on the other, we see that the blue tells us the position of the galaxy at some time, and the red is the same galaxy at a slightly later time. Of course, this is all exaggerated, the amounts of travel, but this is what it looks like. And so therefore, we see all galaxies receding away from from us. And this is how we know that the universe is expanding. And this is true no matter where you go. For example, instead of living in the bottom left galaxy, if we now live in a different galaxy, let's say somewhere in the middle, say shown by the blue one on the right-hand side, and now if I again superimpose, this is what it looks like for an observer in that blue galaxy. So even for that observer in a different galaxy, everything is receding away from their galaxy. And this is true for any point on this picture. The rate at which this recedes is the Hubble rate. And the fact that this rate is not constant, but rather increasing as you go back in time. So the rate has been increasing as a function of time. Previously it was less, now it is more. This is the phenomena called accelerated expansion of the universe. And the way to explain it is to say that 70% of our energy in the universe is in the form of something that is known as dark energy. It's just a name because we don't know where it comes from. There is a guess. The guess is that it is something called the cosmological constant that Einstein's theory of general relativity allows. And that's a perfectly reasonable explanation for why this is happening. And only 30% of the energy is in the form of things like matter and radiation and stars and atoms and neutrinos and dark matter, all of that. So the way we know it is this, that this red curve is what our universe looks like. And that's the fact that it's accelerating and going up like that. Okay. So therefore, we know from all of these observations that our universe is roughly 70% energy of the universe is dark energy. Approximately 30% is dark matter, and much smaller amounts of things like, other elements like hydrogen and helium, stars, neutrinos, heavy elements, whatever. So this is the cause of the famous statement that only 5% of the universe is known, and the 5% is this top 4 squares that you see on your screen. The other 95% is either dark matter or dark energy. But if you confine your attention only to the part that is matter, so therefore remove the dark energy part, out of this 30%, so to say, 5% is, let's say, ordinary matter, and 25%, let's say 27%, is dark matter. So the amount of dark matter is approximately 5 times larger than ordinary matter. Okay? So this is what we know, that there is invisible mass. This invisible mass exceeds the amount of visible mass by a factor of 5. And it is distributed in galaxies as halos that extend beyond the galaxy and over the large scales of the universe in this cosmic web. So this is all that we know. Now the question is, what is this dark matter made of? Now, this is a very fundamental question. This is a question that we have been asking for 2000 years at least. So let us first rule out what dark matter is not. So dark matter cannot be small planets or large planets that we are unable to see, or some kind of cold stars that are hard to see, or even black holes. Why? Because early in the universe was very hot. Stars had not formed, planets had not formed, nothing had formed. And all of this dark matter would have been, available to the universe at the very beginning in its baryonic form, in the form of protons. Let's say if everything was made of ordinary matter, it would have been available at the time that this plasma was oscillating. But we know from this very early data that already at that time, there was dark matter. But planets, stars, and black holes had not formed then. So how can dark matter be made of these objects? It's a simple argument. There is a little loophole to this argument, and it has to do with this idea of a primordial black hole. The fact that very early in the universe, there can be a region of space which has a little bit too much density, and it just collapses into a black hole. And we don't, so this is a different formation mechanism of black holes than the usual one where a star, a supernova, blows up and the core of this star then collapses into a black hole. That way of making black holes cannot explain dark matter. However, if dark matter were to be explained by what is known as primordial black holes, which is to say that it's just early in the universe, density fluctuations lead to collapse of objects. That can explain dark matter. We have already studied this possibility in great detail. It is not known what is the size of these black holes, primordial black holes that could be dark matter. So you look for all possible sizes. What you see on the x-axis, on the horizontal axis, is the mass of these objects, spanning an extraordinarily large range, all the way from 1,000 times the mass of the sun to 10 power minus 18 times the mass of the sun. It's an incredibly large range. And all these colored shaded regions are masses where primordial black holes cannot be making up dark matter. The reason is simple, because on the large mass end, if there are all these black holes floating around in the universe, they would lead to lensing. You would see light bending around it, and we don't. And on the left, the colored plots, they rule out very light primordial dark matter, because these very light black holes have high temperatures. This is one of the key things about black holes that were pointed out by people like Bekenstein and Hawking. And then these tiny black holes radiate using Hawking radiation. And as a result, they evaporate and just die away. Also, while they're evaporating, they're emitting particles like electrons and positrons and neutrinos and photons that can be detected using modern telescopes. So all these colored regions are ruling out masses of primordial black holes, forming some substantial fraction of dark matter, because we don't see such radiation coming from anywhere. We don't see the Hawking radiation. But there is this gap region between, let's say, 10 to the minus 16 solar masses and 10 to the minus 11 solar masses, roughly here. This is roughly the mass of the moon, a bit less than the mass of the moon, something like the mass of an asteroid. Primordial black holes of these masses can be dark matter, but there are no very well motivated theories for making it happen. However, this is an incredibly exciting area because black holes are being looked at using gravitational wave detectors across different mass ranges. And you will hear a lot more about black holes from Professor Bala here. Another thing that we know about dark matter is that it does not interact with itself too strongly. We know this because there are some examples that have been observed of galaxy clusters that pass through each other. Okay, so what is being shown here again in false color, the blue is the dark matter part of these two galaxy clusters, and the red and yellow are the ordinary matter part. And you can see the ordinary matter part has collided, and that has led to these shock waves. The way it happens when a bullet, let's say, goes through water, you can see this shock wave, or when a fighter jet goes through air and it creates these shock waves around it. But the blue stuff does not have any shock waves. And that's the proof that dark matter does not interact with other things, but it also does not interact with itself too much. Okay. Another aside is that you could say that, well, all of this evidence for dark matter is coming from using this F equal to ma law. And that's how we measured the mass that exists. It's all inferred mass and inferred using F equal to ma. So you could say that, let me change F equal to ma. Now, maybe Newton's laws are wrong. Maybe masses are all fine. Whatever we see is what's there. But Newton's laws don't work. And they don't work in a very specific way. That they don't work when the accelerations are very small. When accelerations are extremely small, smaller than 10 to the minus 10 meters per second square, then F equal to ma should be changed by this. So this scale A0 is a fundamental constant of nature proposed by Milgrom. It's of the order of 10 power minus 10 meters per second square. And then you can see that when the acceleration is smaller than that, this term becomes different from 1. This idea is able to explain the rotation curves of the galaxies, but it cannot explain the nature of CMB, the oscillations in the CMB that we see. So although this is a very beautiful idea and many people like it, this does not eliminate the need for dark matter on the cosmological scale. Okay? So that brings us to this notion of what is dark matter. We want something that is stable because it has survived until now. It must be neutral because otherwise, the charged particles interact very strongly with light and we would just see it. It must be weakly interacting with itself and other things. And it must have small velocities. Cold means that it is non-relativistic. So it must be stable, it must be neutral, it must be weakly interacting, and it must be cold or non-relativistic. So is there such a particle? So this is the standard model of particle physics that Professor Godbole talked about in the morning. This is like the periodic table of all the fundamental particles. And it turns out that none of these particles can be dark matter. Why? Because either they are massless, which is the case for the gluon, the photon, or the graviton, or they decay very quickly, like the W or the Z or the Higgs, the the charm, strange top bottom quarks, the muon or the tau, or they are charged, like the up, down, or the electron. So all of these are ruled out. One of the candidates, these three neutrinos, in principle could be dark matter, but we know that they are very light. And if they're so light, then they travel at very high speeds in the early universe, and they would have smeared the structure out beyond what is seen. And that tells us that neutrinos are also not dark matter because they are not cold. Okay? So none of these known particles can be dark matter. So then this brings us to the last part of the talk, which is okay, so we know that there is such a thing called dark matter. We know that it has some properties, that it is stable, it is neutral, it is weakly interacting, it is non-relativistic. And no known particle can explain it. So what can we do? So this is the really interesting problem that now is front of us astroparticle physicists. We combine our knowledge of particle physics and astrophysics and cosmology to solve this very important problem, that what is the nature of this invisible mass that surrounds us? And at this point, we don't have answers. We don't have answers which are compelling that, okay, I can tell you this is what dark matter is, but there are many ideas. And based on these ideas, there are different ways of looking for dark matter. So the very popular idea is that dark matter is a particle, like the neutron. So let's say 100 times the mass of the neutron, neutral, but has quite a bit of mass. And it has the ability to annihilate with itself. So there are two particles of the same kind, let's say X and X, can combine and give two standard model or two known ordinary matter particles, shown here in blue. And the opposite is also possible. It turns out that if you start the universe with having quite a bit of such dark matter, as the temperature of the universe falls, it falls below the mass of this heavy particle. So ordinary matter particles cannot now combine and give you this heavy particle, because that's, you don't have enough energy to make these X particles anymore. But the X particles continue annihilating to standard model particles until the universe becomes so big and so dilute that in some given region, in one mean free path, to be precise, you are left with just one of these X particles. So it can't find a partner to annihilate against. And so then the number of these dark matter particles is frozen. And that gives the final amount of dark matter. Turns out that this very simple idea, when calculated, leads to the precisely observed amount of dark matter in the universe if the interaction strength between these dark matter particles is roughly at the same level as what is there in weak interactions, in the interactions that are responsible for radioactivity. So then that tells us that maybe this is a good idea, and we should look for such dark matter, weakly interacting massive particles. Another idea is something called asymmetric dark matter, where you try to replicate what you know about ordinary matter, that there are protons and there are antiprotons, the antiparticles. They annihilate, and a little bit is left over, and that's the amount of the protons and baryons that we see in the universe. So similarly, they would say that, well, there was something called dark matter and there was something called anti-dark matter, and they annihilated and made a lot of energy, which is what we see today as photons. And there's a little bit of excess, which is now seen as whatever is dark matter. Again, here you would have some particle of some mass. And both of these ideas, the WIMP or the asymmetric dark matter ideas, correspond therefore to some particle of mass, let's say 100 times the mass of the neutron. There's a big range of masses. In fact, we don't know the mass very well, but they have this property that there's some particle with some mass and it has some interactions. It has interactions with ordinary matter. And so therefore, we can look for such particles. How can we look for them? One idea is that this is the Earth, of course, not to scale, sitting in the Milky Way galaxy. We are about, I think, 8 kiloparsecs away from the center of our galaxy. And there is a huge amount of dark matter in the galaxy. So consider one of these dark matter particles and consider a proton in my lab in some very carefully created environment where I've kept it very cold. So the proton is very, very stable. Now, this dark matter particle is traveling at non-relativistic velocities, and it can come to the proton in my lab. Because it is non-interacting, very weakly interacting, it can pass through many light years of material, in fact, all the way through the Earth, and then reach my detector, which is deep underground. There is some small probability that it will now interact with this proton. Just bump into my proton and just kick it. It's like carom. Okay? And I observe that a proton that was supposed to be sitting quietly in my apparatus in my lab suddenly got kicked. This is called a recoil. And I can measure the speed at which this proton got recoiled in the nucleus of some elements, xenon or something. And the rate at which this happens and the velocities with which these recoils happen then tell us whether or not dark matter particle has impinged on my proton. This has been looked at for the last 2 decades almost. There have been ups and downs in this field, but it is fair to say that there is no compelling evidence that such an event has been seen. So we've looked for such events. On the x-axis again is the mass of this particle in units of, let's say, the proton mass. And on the vertical axis is the interaction strength. And these lines are telling you all the region above these lines is ruled out. So it tells you that you cannot have dark matter of such and such mass interacting with such and such interaction strengths. So we've not seen dark matter by using this technique, but I think the game is still on, and we will see where it takes us. Another technique is, now imagine that there's a satellite around the Earth, and it is looking at the dark matter halo, either in our galaxy or elsewhere. And there are 2 dark matter particles there which annihilate and create some observable particles like, say, electrons and positrons. You can look for these particles using our available telescopes. And instead of electrons and positrons, you could be looking at neutrinos, photons, whatever. You could be looking at the objects can be different. You can look at the sun, Milky Way, dwarf galaxies, clusters, the entire sky, what have you. So there's a lot of choice. And all of this is being done and has been done. And unfortunately, again, we haven't seen anything. Again, these curves basically show you the regions of mass and interaction strength, which are ruled out. Everywhere above these lines, we can confidently say that dark matter cannot have those properties. So again, we haven't seen dark matter using this technique, but maybe we just need to be a bit more patient. Or maybe that this idea of a very heavy dark matter with interactions is not correct. Maybe dark matter is something else, a different kind of a particle. These are all beyond the standard model hypothetical particles. So we don't know which one is correct. So a different idea is something called an axion. An axion is a very light particle, less than, let's say, 1 millionth or at least 1,000th of an electron volt. So, and this particle is a boson. It's not a fermion, as it's a spin 0 particle. And so this very light particle can be dark matter. And this particle also is very well motivated from some other arguments having to do with the lack of violation of time reversal in quantum chromodynamics. The fact that in the world of strong interactions, you can't tell whether time is running forwards or backwards. You know, in the fundamental Lagrangian, there is no violation of what is called CP symmetry. And again, there are different ways of looking for this particle. It's a very, very exciting area these days. And they use very beautiful technologies having to do with superconductors, quantum computation technologies, radio, and cavity physics. So all of these engineering tools are used to look for this axion dark matter particle. Again, nothing has been seen so far, but these are early days, and there is a lot more progress to make in this field. So it's a very promising time. Okay, LHC has been running, and one of the things that was expected and promised was that, well, LHC would make dark matter. That hasn't turned out to be true so far, but we are still not giving up. LHC will run for another decade or two, and if we are lucky, maybe we will be able to see dark matter produced at LHC. Finally, there is also the possibility of studying particle properties of dark matter by looking at the universe, by looking at the properties of galaxies and galaxy clusters. So here, for example, on the left-hand side, the horizontal axis, the x-axis, is the distance from the center of the galaxy. And on the y-axis is the density of the galaxy. Both of these are in log scale. And all the dots and the symbols that you see are observed data. The thin lines up here that you see going up diagonally are predictions where if dark matter did not have any interaction with themselves. Whereas if dark matter had a little bit of interaction with each other, not too much, because that's ruled out by this observation of the bullet cluster that we talked about, but a little bit of interaction, then that shape of this density curve or the density profile, it bends towards the core of the galaxy and it flattens. And that's actually what is observed. So a lot of people are very interested in this idea that maybe dark matter has some non-negligible interactions with itself. And observations of galaxies can tell us about that. So this is also a very exciting idea. And it uses the universe or the cosmos as a laboratory for studying dark matter. This is in the typical style of astroparticle physics. Okay, so that's all I wanted to tell you about. Let me summarize. There is overwhelming evidence for dark matter, a variety of scales. We know that it exists. We know that there are many different ways of convincing ourselves that there is dark matter. We know that it exists as a particular, let's say, dark matter halo around galaxies and in some cosmic wave on the largest scales. We know that the amount of dark matter is 5 times larger than the amount of baryonic matter. We know that this dark matter, if it's not a primordial black hole, which is an exception, it has to be a new particle. And this new particle, whatever it is, must be stable, must be neutral, must be weakly interacting, and must be non-relativistic at the time that it was produced. These are non-negotiable. But even though we know these things, we still don't know what it is. So there are ideas. I told you about a few ideas. So there is this idea of dark matter being a heavy particle, either a WIMP or an asymmetric dark matter, or it could be a very light particle like an axion. So they are totally different, and there are many different technologies to look for each of these ideas. There are other ideas. For example, dark matter could be a sterile neutrino of approximately 7 keV or something, and you would look for that using X-ray telescopes. I did not tell you about that, but there are other ideas. So, but these are the most prominent ideas: the idea of a WIMP, an axion, or a sterile neutrino. And you could look for this dark matter in a variety of ways. You could look for this dark matter by trying to observe a recoil of ordinary matter because it has been impinged upon by dark matter from the galactic halo, or dark matter could be annihilating in the galaxy or decaying somewhere and producing observable signatures. Or you could try to create dark matter in the lab, let's say in LHC, or you could use the universe of astrophysics to study the particle properties of dark matter. So these are uncertain and challenging ideas. There is no guarantee that we will find out the nature of dark matter. But I think this is an intensely exciting time to be working on this really, really difficult but exciting problem, which leads us to one of the most fundamental questions about the universe and ourselves, which is that what is the universe made of? And this is a question that we have asked for 2000 years and answered again and again. And each time we have learned something new. And I think it's really amazing that we get to be a part of this great adventure once more, to be able to answer the question of what makes up 80% of matter in the universe that is invisible. Thank you very much. That'll be all for me today. I'm happy to take questions.
Thank you so much, Professor Dasgupta, for this wonderful talk, I would say. You have explained so nicely. So this is now time for questions. So you can either type your questions in the question bar, or you may also raise your hands. So you already have a couple of questions. So first question from Shaunak. So he is asking that how could you superimpose red galaxies to blue as in slide 1? If light could not reach from red ones, then how could we know its distribution? Are we superimposing two different time scales? It has three questions, I would say.
Yeah. Let me see if I can answer your question. I imagine that you're talking about this dark energy slide.
I
This
guess,
one.
yeah.
Yeah.
The expanding
So
universe.
the expanding universe. So this is just a demonstration. All I'm trying to do is give you a visual uh, feeling for what it means for the universe to be expanding. It means that no matter which of these galaxies you are on in these blue galaxies, standing in any one of these galaxies, you see all the other galaxies receding away from you. And because it's receding, we know that there will be a redshift, which is why I have colored it red. This idea of superimposing is simply to show that each galaxy sees the same thing. That if I am, let's say, on this galaxy that is blue in both pictures and then superposed to the one which is over here.
Are you sharing the slide? It is not shared
Oh,
with me.
is it? Oh, how did that get
No,
unshared? I don't know how
yeah,
that happened. Let me share my screen again.
yeah.
There you
Yeah,
are.
yeah.
Do you see my slides? Good.
Yes.
There
Yeah,
we are.
this, yeah.
Okay, so let's say we are on the bottom left galaxy, and the one on the right hand side is the same thing, except that now I have deliberately colored all the other galaxies red because they're red shifting away from us. And this act of superposition is simply to demonstrate to you visually that I see all the galaxies receding away from us at a rate proportional to their distance from us. This is the meaning of Hubble expansion. But you see, this is not typical to our galaxy, which in this case is the bottom left one. This is also true if I were sitting on some other galaxy, let's say the one which I'm pointing at now. So for that, all I would have to do would superimpose that galaxy on itself and show that all the other galaxies are receding, which is what I do now. So now I am in this galaxy, this blue one, which is colored blue on both of them. And now if I superimpose, look at what happens. Now that one stays where it was, and and that galaxy sees every other galaxy receding. Okay, so this is a visual demonstration of the fact that the expansion of the universe does not favor any observer. Any observer anywhere in these galaxies would see the same thing. Okay, and we are not superimposed two different timescales. All we are saying is that no matter where we are, no matter which galaxy you are on, you see other galaxies on average recede away from you. And I am just using this superposition as a simple visual way to convince you of this fact. Is that clear?
Sono, can you hear us? Is the answer clear to you? You can unmute maybe.
Maybe we can come back.
Yeah.
It's clear. Now you can. It's clear. Okay, perfect.
Thank you.
So next question, I would say there is a confusion here. Okay, let me tell you the question. So in the multiple moment animation slide, you said 10% dark matter tuning is required to make the two peaks equal, but the dark matter proportion is approximately 27%, as you also pointed out. Was that dark matter content of early universe? If yes, so you understand the confusion. Yes.
Thank you very much. This is a good question. I apologize for the slightly confusing remark. Well, I said wrong. What I said was 10% is not the fraction of dark matter, but the fraction of dark matter multiplied by the Hubble parameter squared. This h is approximately 0.7. And so when you square 0.7, it becomes 0.49. And so 0.3 times 0.49 is approximately 0.15, which is this 10% that we are talking about. So, all things considered, omega m has to be of the order of 0.27. H square has to be of the order of 0.5, let's say. And omega m times h square has to be of the order of 0.12. So these are the correct numbers. Sometimes colloquially, when we say that the fraction of dark matter is 0.1, it's a very bad use of terminology. I apologize. What I actually mean is omega m h square is 0.12. So thank you for catching that. So nothing has, omega m h square is 0.12. Omega m itself is roughly 0.27.
Yeah, I think it's just representation. It's almost the same.
But good. Thanks for catching.
Good point out. Yes. Anyway, okay. So the next question is, you talk about dark matter as halos around galaxies. What we observe beyond this dark matter region? What we observe, And is there any specific reason that dark matter attached to these galaxies?
Very good. That's a really nice question. So
Amarendra
you're saying,
Verma. Yeah.
okay, that's a really nice question. The question is that I am claiming that galaxies live in a halo of dark matter. And the question is, what is there beyond the halo, firstly? And why do dark matter halos attach themselves to galaxies? Okay, so let me first answer the first question, which is what is there beyond the halo? Beyond the halo, truly we believe that there is nothing. So there is a dark matter halo, which inside which there is a galaxy. There's another halo, and then sometimes these halos are connected by these filaments of dark matter and so on. But so to say, there are indeed regions of what we would call void. These regions we really believe are truly empty. Okay, so the answer to the question, what is beyond the halo? Nothing. The second question is, why do galaxies attach themselves to dark matter halos? Now, this is a very good question. In fact, this is really at the heart of this idea that the large scale structure of the universe tells us about dark matter. So what has happened is that early in the universe, dark matter formed the structures first. It formed this big network of filaments and halos and things like that. And ordinary matter fell into the gravitational potential well created by these dark matter halos. So it's very natural that wherever there was this big halo blob of dark matter, that is where the ordinary matter also got captured. And then once it fell to the center of this halo, it ignited, formed stars, planets, everything else. And that's what we see today. So it's not so much that the halos attach themselves to the galaxies, but rather the opposite, that the galaxies preferentially form at the center of halos. Excellent question.
Okay, so there is one more question which is connected to the first question. This is from Subham Pandey. So he's saying that what is the evidence that all galaxy observe, or maybe observation, would see the same expanding universe in all directions?
Very good. There's again, depending on how, let's say, how knowledgeable you are about this subject, I can give you many different answers. But let's give the simple answer first. Simple answers have the good thing about them that we at least understand what we are talking about. Of course, they have the problem that they're not complete, that there are hidden things that we are not telling you about. So let's first give the simple answer. The simple way to do it would be take a telescope, point it at different parts of the sky, measure the redshifts of galaxies, away from you. There will be some galaxies that are coming towards you because galaxies are not static in this cosmic frame. Rather, they're like gas molecules. They could travel in any direction they want. But on average, if you average over a sufficiently large number of galaxies, you will find that in any direction, these galaxies are moving away at a rate that is determined by their redshift or their distance from us. Okay, so that's easy. You can just build a big telescope, make your measurements, and convince yourself that this is true. Now, what is the problem? The problem is that this is very hard. This is very hard to do. There are many things to be careful about. There are some people who do not believe that the universe is expanding equally in all directions. These are very, I would say, these are not things that are as well studied as most of, let's say, modern cosmology. So but there are, let's say, at least some groups who question this assumption of isotropy on cosmological scales. And yeah, the way to establish this is observations. You make careful observations and convince yourselves that indeed the universe is expanding in all directions equally.
Okay, so the next question from Anukar, it's a very interesting question. So the question is, the dark matter halos look like a diffused gas all around the galaxy. Why don't the halos collapse under their gravitational influence?
Very good.
Very good
Okay,
question.
that's an excellent question again. Question is that why don't these dark matter halos, collapse into a black hole, let's say? Very, what, that's what would happen if it really collapsed. It's a very important question. And the answer is that it has to do with conservation of angular momentum and conservation of energy. So consider a bunch of bunch of particles that are whizzing about each other with some velocities. Because no force from the outside is acting on this blob, its total energy and total angular momentum must be conserved. Now, angular momentum conservation often means that there is some direction, some preferred direction in which the total angular momentum lies, and stuff can whiz past a plane perpendicular to this direction, and eventually it can flatten itself out into a disk. And this is how, for example, galaxies become, these spiral galaxies. They become these flat galaxies. You can lose angular momentum if there is some dissipation process like that. To really compactify, to really go in the center, you need to lose kinetic energy in some way. And the way ordinary matter loses this energy and angular momentum is by emitting photons. Stuff collides, electrons and protons or whatever will collide, and they will make photons which escape this system. And this continual loss of energy from photons and angular momentum is what leads to formation of compact structures in ordinary matter. But dark matter does not have such interactions with photons. And that is why dark matter halos cannot collapse so easily. In fact, that's one way in which we know that dark matter does not have interactions with these light particles like photons.
Okay, so there is, it's not a question, maybe it's a comment. So maybe you can comment on that. So it says that all this is based on our assumption that the superposition of forces works like it does in simple cases. Maybe it doesn't. The force of gravity doesn't follow the superposition principle, and thus our answer, maybe mathematically, doesn't
Indeed.
match with the observation.
That's actually what I hinted at. That's a good point. Let me just get to the slide and I will comment on that again. Yeah. So the point being made here by anonymous attendee is that maybe this is all happening because forces don't add the way that we think they should. So you have to explain why they should not add via superposition. There needs to be some change. You have to, whenever you are attacking some idea, you have to also provide me in what direction do you want me to modify this idea. And so the only, reasonable, well-known, let's say, way of, making this point concrete is modified Newtonian dynamics. Now you see this has the property that is being talked about. If the equation was F equal to ma and this bracket term, the red underlined term was not there, you can see that this is a linear equation. If you have this F equal to ma, and let's say you have another one called F2 equal to ma2, and you can add these equations, F1 plus F2 is equal to m times a1 plus a2, right? So forces add, accelerations just add. That's linear superposition. However, once you have this extra term in the bracket, if you add the forces, accelerations are not just the sum of the accelerations produced by the individual forces. The equation is much more complicated. In fact, any of you who know differential equations, will immediately see that this is a really complicated nonlinear differential equation. No, A is d2x dt square. So this expression on the right-hand side is actually quite complicated. And it certainly is not a linear equation. There is certainly no linear superposition of forces. True, that's a possibility. But then it would become the job of whoever is proposing this idea to explain all the observed data about dark matter the way the hypothesis of dark matter explains this data. So there is all this data that I told you about, and it's explained by dark matter, this hypothesis of some invisible mass. It explains it on all these scales. There is no other theory that does it. So that's the reason why we don't take this idea very seriously.
Okay, so Shubham Pandey has another follow-up question. He says that if dark matter has mass and hence gravitational interaction, could they also make large-scale structures, say stars or black holes, made purely out of dark matter particles?
Indeed, yes, that's possible. In fact, there are claims that there are such objects. They're not very well-established claims, but indeed there can be small galaxies that are purely dark matter.
Yeah. Okay, the anonymous attendee has another question. It's the same, I don't know, but it says that if dark matter doesn't interact a lot with itself, why is it that they form clusters?
Because of gravitational interactions. The gravitation interaction is very weak, so dark matter can cluster gravitationally, but these interactions are not as strong as what would be provided by electromagnetism or strong interactions. So therefore, although they're weakly interacting, they still interact via gravity, and that's the reason they cluster.
Okay, maybe the last question is that if there is a source of light, like stars, for example, can there be also a source of dark matter?
So you want something to be making dark matter. Yes, that's kind of what was hoped for by, let's say, in LHC, where you collide protons and you hope that out of that debris of this collision in the Large Hadron Collider, you would make a few dark matter particles now and then. So it's possible. The laws of physics allow it. This has not yet been seen.
Yeah, I guess we have answered all the questions. So right. Yeah, I think it's time to thank you. It's a super talk, and thanks to all the participants as well. And so maybe we will take half an hour break and we will start the talk from Professor Bala.
Amit, yeah, can I ask a question?
Yes, absolutely.
See, I am Professor Durga Rao and I am a biologist. I am not a physicist. And it's a very nice talk that a biologist could understand your talk. I have some, I might sound stupid in asking this question, but, it is, I'm thinking about after your talk. You said dark particles do not interact with each other, okay? And they are held, yes, you said also by gravity. But if they do not interact with each other, they should also be moving out rather than being compact, actually. So is that the reason that the galaxies are also moving apart, because of the dark matter is also expanding?
Yeah, sorry, I mean, there are many things here, and indeed, I apologize if I wasn't totally clear. Dark matter does not interact with itself or other particles at the level at which ordinary particles interact with each other. Ordinary particles interact with each other a little bit more. Dark matter particles only interact with each other, as far as we know, gravitationally. This is sufficient for them to form the structures that we see, these halos. The fact that these galaxies are going further away from each other has nothing to do with dark matter as far as we understand it. It has more to do with the fact that the universe itself is expanding. And that's like, so okay, so imagine there is a very big rubber sheet. So there is a huge football stadium sized sheet of rubber. And I ask children, to create little, mounds of sand by collecting sand which is on this rubber sheet. And I think of these mounds of sand as galaxies made of dark matter. So you can create a little mound of sand locally around you, and you will be very happy. But your friend who's sitting on the same rubber sheet far away, and I'm stretching this rubber sheet as time goes on, will be moving further away from you. So I can locally start collecting a lot of material and pile it up into a mound, which is this dark matter halo. This is what the gravitational interaction of dark matter does locally. But the universe is like this stretching rubber sheet. The universe is becoming bigger and bigger. And so the distance between these mounds of sand keeps increasing with time. And that's the equivalent of the galaxies moving further away from each other. So they come from different causes.
Okay, thank you. Anyway, it is beyond my understanding. But what I was thinking was, if the individual galaxy is also expanding, the surrounding halo also must be expanding. So the dark matter also must be expanding because it's loosely bound. Maybe the gravity may be helping. That's what I was thinking. Okay, thank you.
Thank you.
Okay, thank you, Vasudev, for this nice talk.
All right, thanks for the lovely interaction, and all the best to your new and exciting department. I hope you guys do a lot more of these events, and I hope that there is a lot of excitement for high energy physics, cosmology, astroparticle physics, both in your department and your university. So yes. Thank you, everyone. Thanks a lot.
Yeah, thank you so much, and take care. Yeah,
you too.
Bye.
Bye.
Yeah, so we'll meet at 4.
Carrying out research in frontline and emerging areas of science, technology, liberal arts, and social sciences. I'm glad that faculty members and research scholars of this university have published 241 quality publications in the year 2020. Some of them appeared in Nature, Nature Microbiology, Proceedings of National Academy of Sciences, PNAS, Applied Catalysis, and IQB journals. Members and students have filed and published 11 papers in this category. Other members for the lithium batteries, also developing 3D printed battery terminals. more farmland. Hello, I'm Dr. Sudarshan Govindarajan, Assistant Professor at the Department of Biology. The low-cost alternate cathode materials, then the adopting of additive manufacturing, that is, we have come up with an idea with a more than 5 That only when R&D and innovation system is strong, Indian R&D, Indian industry depends on the foundation of the working at the very frontiers of science. Excellent. Let me start with principles. In the year 2021 and so for their publications, and especially about 50 publications will come from electric GE, especially for 3D printing of gold jewelry. Further, we will start.
Hello.
Hi, Amit. Can you hear me?
Yes, sir. I can hear you.
Okay. I just wanted to check,
Yeah.
is it going, if it's a webinar, I think breaking in between will not work as well, right?
No. I think this is some
Very high
recording
impact.
version that our ITKM section is displaying. So that is maybe the video has some issue, but that is fine.
So we are using a standard Zoom in conference.
Yeah. Yes.
Okay. And I could not hear that very clearly, so I was a little worried.
I understand. Yeah, I understand. No, but we had all the previous two talks and it went very well. I mean, there was no interruption.
Okay. So now you can hear me also clearly.
Yeah, yes, sir. We can hear you.
Okay. So shall I share the screen then?
Maybe,
Or
or
wait?
you just, maybe just we'll wait for 7 minutes.
Okay.
So
sure.
the session finished 5 minutes before in the last session.
Oh.
So there was many question answers session.
Okay. I see.
Yeah. So.
So what do you, based on your experience for the morning two things, do you think we should just finish the full talk and then take the questions in terms of your logistics? That's simpler?
Yeah, so last two talks went like that. They took questions at the end. Or I noticed that in between there were a couple of raised hands. I mean, maybe they had some questions at middle. So maybe what we can do, we can pause in the middle somewhere, wherever you feel.
Okay.
And at that time, if we have any question, then maybe we can take
Okay.
one or two questions. And then at the end, we can keep all the questions, whatever we have.
Okay, very good. So we'll try that once. Yeah.
Yeah. So whenever you feel that you can stop and take questions.
So as I said, in my presentation, there is a first part which is called gravity wave primer. So once that ends, we will ask for questions if somebody wants any clarification.
Yeah.
And then go to the next part of the talk, which is basically the results, which use all the things which I explained in the first part. And then the last part, which is about the future.
Okay. Yeah.
So if, I don't know how hard is your end of the talk. So I leave it to you, if you want me to wind up.
No, I think this is fine because we had pretty gaps in between. So because there's only one talk in the morning. So it's just only one talk after lunch. So I hope this should be okay. That should not be any problem.
Okay. But as I said, as a chair, you just give me a warning about, winding up the thing up in 5 minutes or something like that.
Okay.
Because, being in a room by oneself, one loses one sense of time, etc. So as a chairman, do exercise the privilege to say that we should end the session.
Okay. Maybe before 5 minutes, I will just
if you think, for example, my presentation is going on too long, because then, there are additional slides which I can just skip and go to the essence. So I can use my discretion if you feel that it should wind up so that we can have questions or something like that.
Yeah. Okay. So this is at least the plan is you have 1 hour for this whole presentation, and then depending on how many questions, then we can go ahead. So maybe I will give you a ring around 55 minutes.
Yeah, but with if you're going to break in between, that will you'll have to change the strategy for a little. So the way it is, how I thought it is 1 hour plus for questions. You have been leaving about half an hour for discussions, right?
Yeah, something like that maybe. So I mean, maybe 1 hour.
And we'll just see how it goes.
Yeah,
Sometimes
yeah.
there is so much, there's so much dead silence that we have to close the session anyway.
Yeah, that's no problem. Yes, no problem.
So you are using also YouTube streaming or only the Zoom?
No, YouTube and I guess Facebook.
Oh,
So,
I see.
So all these two are live streaming.
So the questions from there you will be monitoring, is it, and then telling me?
So far I am taking only questions from here. So
Okay.
I'm not getting any question from there.
Okay.
Yeah. So whoever asking here and maybe raise hand, I am taking.
So all the students of your university are joining by Zoom mostly, most of them.
Mostly at Zoom. Yeah, mostly at Zoom. And the outside people, because I saw many registrants from IIT Madras, IIT Bhubaneswar, IISER Pune. So they all have registered, and so they will receive the link accordingly.
Okay.
Directly some Zoom link.
I see.
So they will also join.
Where exactly is your campus, Amit?
So this is half an hour from the Vijayawada station.
Okay.
So this is yeah. So this is Amravati, the new proposed capital actually.
Okay.
So this is the capital area region. But as you may know, maybe that there are some political issues going on regarding one capital versus three capital.
Right.
So that hasn't decided yet.
I see.
So that's the situation. But this is supposed to be the middle of the capital region, Amravati. So there are other campuses like nearby VIT Andhra Pradesh. They have their new campus here.
I see.
And Amrita University. So they are also building up a new campus nearby. So it is supposed to be a educational hub.
I see.
Some universities will be. I mean, it's already there. VIT and SRM has already working well. Amravati is still in under construction.
Okay.
So yeah. So maybe we'll start within 1 or 2 minutes.
Okay.
So maybe we'll start the session now. So welcome back to all the participants for the last session of this symposium. So we have with us Professor Bala Iyer from ICTS Bangalore. So Professor Iyer is a well-known scientist internationally, both nationally and internationally, in the field of gravitational waves astronomy. So he is currently at Simon's visiting professor is at ICTS, as I said, International Center for Theoretical Sciences in Bangalore. And also before ICTS, he worked at Raman Research Institute, RRI, Bangalore for almost 3 decades or so. And he worked on astrophysical applications of general relativity, perturbation methods, and black hole. Especially his notable works includes calculation of gravitational waves from inspiring binaries of neutron stars and black holes. Professor Iyer has been the chair of the Indigo Consortium, which was proposed in 2009. And so basically he was chair from the very beginning, and also the principal investigator of the Indigo's participation in the international collaboration called LIGO Scientific Collaboration between 2014 to 2019. And he was also the core member of LIGO India mega project proposal. And also in apart from his research works, which are internationally acclaimed, he is also chief editor and subject editor over different reputed journals in the field of astronomy and astrophysics. And he also has been visiting scientists at different places outside India, in France, in UK, Germany, and USA. And he's also a fellow of American Physical Society, and importantly, an International Society on General Relativity and Gravitational Waves. So he has been a known face for some several decades now, I guess, over in the public outreach. So it's my immense pleasure to invite Professor Bala Iyer to give us this very interesting talk on detection of gravitational waves and multi-messenger astronomy. So Professor Iyer, please start.
Thank you, Amit, for this kind invitation to share with the audience a very interesting development which has happened over the last 5 years. So before I begin to share my screen, let me thank all the participants who in these trying times have come to listen to this particular talk. So the most important thing is take care of your lives, because it's very hard times at this particular point. So with that, I would like to share my screen. So Amit, shall I go ahead?
Yeah, please go ahead. Yeah, I can see.
I'm just trying to make it full slide for a minute. Okay.
Yes, perfect. Yeah.
Okay. So as Amit mentioned, I'm going to talk about the detection of gravitational waves and how very quickly it has led to the dawn of multi-messenger astronomy. So I decided that since I have a mixed audience, I will begin with a primer on gravitational waves, so that you know in the latter part of my lecture, when I talk about the discovery, the foundations of what we do. As you all know, general relativity is Einstein's relativistic theory of gravity. It is considered even today as the epitome of mathematical elegance, conceptual depth, but most importantly, observational success. In Einstein's view, gravitation is synonymous with space-time geometry and mathematically described by the curvature or the distortion of space-time. Gravity is described by Einstein's equations, a system of complicated 10 nonlinear partial differential equations. In words, those equations say that matter tells space-time how to curve, and in reaction, space-time tells matter how to move. If you take any relativistic theory of gravitation, like the general theory of relativity, it must be consistent with the principle of special relativity. So the effect of gravity cannot be transmitted faster than light. If the gravitational field of an object changes, the changes propagate through space and take a finite time to reach other objects. Because of this, it leads to the possibility of gravitational waves from Einstein's equations, just like we learn about electromagnetic waves from Maxwell's equations. So we can say gravitational waves are freely propagating oscillations of the gravitational field. According to the equivalence principle, uniform gravitational fields can be transformed away. So physically, gravity manifests as a tidal effect. So one can say that gravitational waves are oscillating tidal gravitational fields which propagate out from the source. Gravitational waves were predicted by Einstein in 1916 as an important consequence of general relativity using an approximate version of general relativity called linearized gravity. That means you take only the leading order term in the equations. A couple of years later, he derived what we call as the quadrupole formula, which is the analog of the dipole formula in electromagnetism. This formula says that a gravitational wave perturbation falls off like 1 by r, like any wave. It's proportional to the gravitational constant g. C is the speed of light, and it is determined by the second time derivative of the quadrupole moment. Using this simple formula to a system of mass m moving with velocity v at a distance r, the formula reduces to a very simple combination, which when applied to a dumbbell made up of two trucks of a ton each, separated by a couple of meters, rotating at about a kilohertz, leads to a value of about 10 raised to minus 39. So you can see that this is a very, very small value, and Einstein, being a patent of his clerk, essentially realized that this must have a practically vanishing value in all conceivable situations. Such ripples would be vanishingly small and nearly impossible to detect. So it's not a big surprise that it took 100 years to make the first detection of gravitational waves. The story changed because in 1974, Hulse, who was a graduate student like some of you, and Taylor discovered what we call as the binary pulsar 1913 plus 16. This is a celestial dumbbell, you can say, made up of two neutron stars. So if general relativity is right, the system must emit gravitational waves and spiral inwards. Observations for over about 20 to 25 years essentially shows that the quadrupole formula is verified in this particular case. And for the discovery of this particular object, Hulse and Taylor received the Nobel Prize in 1993. In our story, this is a watershed event because it demonstrated without doubt that gravitational waves are physical and accurately described by Einstein's general theory of relativity. For many years after Einstein's prediction of gravitational waves, there was a lot of controversy whether gravitational waves are real physical waves or whether they are only gauge effects in the particular theory. So this was a very important aspect of which happened with the discovery of the binary pulsar. So now we can ask more physical questions. So we'll look at Einstein's equations and ask what happens to the gravitational waves in the general theory of relativity. And then we can show that the tidal force is oriented either in the form of a plus or in the form of a cross. So if you take a system of circular configuration of particles and let the gravitational wave fall on it, you would find that they would be tidally stretched and squeezed in an oscillatory time-dependent manner. So if you want to detect gravitational waves, you should really measure the amount of squeeze that the gravitational wave is causing. To quantify this, we define the notion of what we call as a gravity wave strain. If you take two test particles which are separated by a distance L, and if a gravity wave signal passing through changes the separation by delta L, you define the ratio of delta L by L, and that is called the gravity wave strain. So if you have a fixed strain, if you want to have a larger displacement, obviously you should have a larger device or a larger length. Now we apply this formula to the binary pulsar-like system. So suppose you had a system of 2 neutron stars in the nearest cluster of galaxies, which is the Virgo cluster, then the strain is of the order of 10 raised to minus 21. So you can compare it. For the laboratory source, it was about 10 raised to minus 39. So by this particular source, you have almost gained 2 orders of magnitude. Now, if you can build an interferometer, which is a kilometer length long, it will cause a displacement of the order of about 10 raised to minus 18 meter. And in an interferometer, any displacement will affect the fringe pattern. So if you really want to detect gravitational waves, this very small strain and this very small displacement, which is smaller than the nuclear dimensions, this is what should be measured to detect gravitational waves. To really look at how big the challenge is, just recall that if you look at the special relativity experiment of Michelson and Morley of 1905, it measures a displacement of the order of about a nanometer. So you can see there is almost 10 orders of magnitude to be crossed. And if you believe that every 10 years you can have a factor of 10, it will almost require about 100 years. And that's exactly what really happened. There is another independent challenge which happens. You want to measure something smaller than a nuclear dimension, but if you put the device on the Earth, there is seismic motion of the order of a nanometer. So unless you can damp the seismic motion by, again, a factor of 10 raised to 10, you cannot really do an experiment to detect gravitational waves. So as you can see, there are these two factors which really challenge us. And this is really the big challenge, experimental challenge to detect gravitational waves. Let me just remind you about what you learn in your course about a laser interferometer. So a laser interferometer basically is shown in this particular animation. There's a light coming out. It is split by a beam splitter. It falls on the end masses, comes back, and creates a fringe pattern. If the arm lengths are equal, as is first indicated in this particular video, you will see the light has gone, hit, come back, and now it's going back towards the output port. And if the arm lengths are equal, there is no fringe, there is no path difference, and therefore there is no light which will come out. There's destructive interference. But if a gravitational wave falls on this particular detector, the mirrors, the arms would be tidally squeezed. One arm will lengthen, the other arm will become smaller, and therefore there will be a path difference, and that will show up as a light, output light in the photodiode. So if you can measure the small current which comes out because of the effect of gravitational waves, then you can really detect gravitational waves. A simple Michelson-Morley effort is not good enough. So what you really need is what we call as a suspended Michelson interferometer. To increase its optical path, you use Fabry-Perot cavities. And then there are advanced techniques called power and signal recycling. And then you design high quality photodiodes. So putting all these two together, you can really have the technology to detect gravitational waves. You can say in a line that the interferometer is acting like a transducer, converting the gravitational wave to a photocurrent, and the photocurrent will be proportional to the strain amplitude. If it's a stronger gravitational wave signal, there will be a larger tidal distortion, and there will be a larger output diode. So this is basically the basic principle which you use. But then you realize that when you try to ask the question, how much, how small a displacement can I measure? The answer depends on the frequency at which you make the measurement, basically because at different frequencies, there are different noise sources. So what is shown here is the sensitivity of this particular detector at different frequencies. And there are different technologies which have to be challenged and sort of to be overcome to really get this particular sensitivity. For example, at the higher frequencies, you achieve this sensitivity by using higher laser power. At the mid frequencies, you have to control the thermal noise, and therefore it is managed by looking at the various coatings which you use for this particular mirrors. And at the lower frequencies, as I told you, you have to beat the seismic noise, and therefore you really need to design the best possible shock absorbers or better vibration isolation. And therefore, by using a combination of active and passive oscillation, you can reduce the displacement by a factor of 10 raised to 10. And putting all these things together, you essentially come up with the LIGO and Virgo experiments, which remade the final discovery. The interferometers are very long, 4 kilometers long. So again, you have to have vacuum in those beam tubes. It's ultra high vacuum, so it's a very large vacuum system. It's a very complicated system, so you really have to have about 300 control loops to make the interferometer optimally run. So all this really is instrument science at the frontiers of physics fundamental limits. And therefore, if you really look at the profile of the scientists in LIGO, it contains not only physicists, it also contains a very large number of engineers who specialize in different aspects of technology. The displacement, the sensitivity which you require is so high that if you see the effect in one particular interferometer, you cannot be sure whether it is because a truck went outside the interferometer or whether there was an astrophysical source. So to be doubly sure, the LIGO project decided to have 2 interferometers put as far away in the US as possible, one at Livingston and one at Hanford. It's about 3,000 kilometers away. So the light travel time is about 10 milliseconds. And therefore, if you think that you are seeing an astrophysical signal, it should be seen both at the first observatory and at the second observatory with a time lag. So the coincident detection between the 2 LIGO observatories is used so that you can be sure that it is not due to some noise at a particular observatory. And at each observatory, again, you have to look at all the sources of noise. So there is a large number of systems which monitor all the sources of noise. So when you get the data, you have to make sure that it is not due to these noises. And then after you are made sure that that is not the case, then you will be sure that you are discovering an astrophysical signal. There is a project similarly in Europe, a French-Italian project, which is called the Virgo. It's a smaller interferometer. It's about 3 kilometers long. So the present observations essentially were made by the LIGO and the Virgo network. Why is this important? It's important because if you really look at a instrument, you really have to ask, what is its frequency response in different directions? Remember, the gravitational waves can be seen by a detector from all directions. So in a sense, the gravity wave detector is like a ear, like our ears, and not like our eyes. You can hear it from, and you can hear sounds from all possible directions. So if you really want to localize a source on the sky and do astronomy, you really need a network of detectors. And that is, once you have a network of detectors, you can use triangulation. And this is exactly what police do if you want to measure, from which particular mobile phone some particular mischievous message is coming. You basically try to localize it by using different towers and do triangulations. So if you have a network of gravity wave detectors, then you can do triangulation and try to locate the source in this particular sky. So having a global network is very, very important to do astronomy. This is all about the detector. Now, even if you make the best possible detector, we face the next challenge because of the fact that even if you have a very strong gravity wave source like a neutron star or a black hole, compared to the noise in the detector, the gravitational waves are weak signals. So as engineers know, you can use techniques called match filtering, by using which you can first detect the signal and then extract it from the noise. And then because you have done a match filtering, you can estimate the parameters of the signal or characterize that particular signal. What is match filtering? What is shown here in this cartoon is the noisy data, and buried in the noisy data is a small, weak, but predictable signal. Now you do the correlation. What you basically do is correlate the noisy data with a known signal. And when you look at the correlation, that means you multiply the data by a known template, and then you look at the correlation. Exactly when you match with whatever is buried here, the correlation is sort of picked up. So you can see here that if you can predict what you are seeing very accurately, the correlation can be strongly picked up. If you cannot predict it very accurately, the correlation will basically drop. So essentially, since you don't know what are the parameters of the particular source, you cannot do it with only one particular template. You basically have to construct a template bank. You have to know what are the parameters the waveform depends on, and change all those particular parameters and create a bank of templates. And the other thing, as I told you, is a challenge from theory. You should know how the waveform really looks like. So you really need an accurate model of the signal. And since our best theory for gravity is general relativity, we should be able to use general theory of relativity to calculate the signal which is coming from a neutron star binary or a black hole binary. Now you come up with theoretical challenges. And the theoretical challenges come about basically because if you have a body which is self-gravitating, that means it's held together by gravity, then what happens is that the potential is of the same order as v square by what is called as the virial theorem. So if you want to calculate the waveform to higher orders of accuracy, you want it as accurate as possible, you really have to make sure that you want higher powers in v square, but higher powers in v square means higher powers in g. So the linearized gravity which Einstein used to derive his formula are not good enough. You really have to face the non-linearities of Einstein's theory. And this was a big challenge when the LIGO project was basically funded. But, Einstein's theory is such a beautiful theory that you can set up an approximation scheme to improve upon Einstein's quadrupole formula. So what is shown here is the gravitational wave phase as, approximately improved by order. The parameter x is like v square. So in a sense, you can correct Einstein's quadrupole formula to orders v7 by c7. And you really need all this kind of accuracy to really make discovery of gravitational waves. So this is exactly the kind of theory which you require to really make the detection. If you look at this particular formula, in this formula you find these very, very large numbers, and you must have seen glimpses of this in the high energy physics talk also. You can use quantum field theory to really make predictions of corrections which come from quantum electrodynamics. So you are basically doing a similar calculation here. And these numbers and these coefficients which come here really come from Einstein's general theory of relativity. So ultimately, you can test Einstein's theory of general relativity because you can try to look at the data and see whether it is consistent with what you are predicting from your theory. It turns out that this simple calculation which you do is not really sufficient. You really have to improve upon it by many other techniques. For example, you use resummation or Pardee techniques. You use techniques which are called effective one-body. When the approximations in terms of post-Newtonian calculations break down when the bodies are close to merger. So you really have to solve Einstein's equations numerically by using numerical relativity. And you try to blend together analytical and numerical calculation by using what are called phenomenological, IMR phenomenological waveforms. And sometimes from the numerical relativity waveforms, you can create numerical, more efficient surrogates. So all this underlies the discovery, which I'm going to talk about in the later part of my lecture. So what you have to keep in mind is that once you have the raw data, there is a lot of work which you have to do to calibrate your detector. There is a challenging work related to that. You have to characterize the noises in this detector. So by putting all this work together, the raw data can be converted into from the raw data, you can extract out the gravitational wave signal. The gravity wave signal depends on 15 parameters. intrinsic parameters like the masses and the angular momenta of these particular objects, and then the other parameters will tell you where the object is located, what is the relative orientation of the detector and the source, and so on. So there are 15 parameters which apply there. So you basically use Bayesian methods to extract out the parameters of this particular signal. So what is shown here is in blue the raw data, and in the red the waveform which depends on 15 parameters, and you basically try to change the parameters so that your model waveform essentially matches as accurately as possible with the raw data, with the gravitational wave data. So by such Bayesian methods, you can extract out the parameters of this particular signal, and therefore this is what allows you. So the match filtering allows you to detect this particular signal and to characterize this particular signal. And therefore, what you really have to keep in mind is that buried in the waveform of a binary black hole, for example, are all the effects which will affect this particular waveform. For example, if the bodies are spinning, then there will be some effect on the waveform. There are effects of backscattering, which are called tails. They will affect this particular waveform. In the case of a black hole, there are horizons which absorb that radiation. That also causes effects on this particular waveform. And once these objects merge, then as Vishweshwara had shown long back, the modes will die down like the sound of a dying notes of a bell by what are called as quasi-normal modes. So you can see here that in this particular waveform is buried all the physics which underlies this particular process, and that is very, very important. We have to contrast it, for example, with what happens if you have a binary neutron star, for example. If you have a binary neutron star, then as you know, they are not as rigid as black holes. So though in the beginning, the waveform will look like the waveform of a black hole, as it comes closer, because of tidal effects, the waveform will depart from the point particle approximation, and the extent of the tidal deformation will be determined by the equation of state of these neutron stars. And therefore, in a sense, from the waveform, you can extract information about the equation of state of neutron stars. And that really is the important point one has to keep in mind. And that is how we do astronomy, by using gravitational waves. The other thing is that if you analyze the equation of general theory of relativity and ask for the properties of gravitational waves, the equations tell you that in Einstein's theory, the gravitational waves travel at the speed of light. Like light waves, they are transverse, and they have two states of polarization, which we call plus and cross. Unlike the case of electromagnetism, there is no monopole or dipole radiation because of the fact that there are conservation laws of energy, linear, and angular momentum. So the leading order radiation for gravity is quadrupole radiation, basically because of the fact that gravity is described by a spin 2 field rather than by a spin 1 field like electromagnetism. But there are other important differences which allow us to do better astronomy. The gravitational waves essentially propagate unperturbed through space because of the fact that the gravitational interaction is 10⁻39 times weaker compared to the electromagnetic interaction. So if you have a supernova kind of event, you can see the gravitational waves from the heart of a supernova. Or suppose you are talking about gravitational waves from the Big Bang, you would be able to see gravitational waves from a very, very early epoch in the universe rather than the electromagnetic cosmic microwave background. So you can see here that there is a lot of information which comes from the gravity wave channel, which is not accessible to the electromagnetic channel at all. As I told you, and again I should emphasize this, the properties which I'm talking about the gravitational waves, they can be different in different theories of gravity. For example, if gravity is propagated by a massive graviton, the speed of gravity will be different. So the properties of the gravitational waves, like the speed, the polarization, and so on, essentially will test the theory of gravity. So therefore, there is eventually the possibility to test Einstein's general theory of relativity in the future when you have more and more gravity wave observations, and you can try to look at the properties of the gravitational waves and check whether they are consistent with Einstein's general theory of relativity. So to conclude my primer, we have a very challenging and what I call as an unforgiving experiment. This unforgiving experiment is what drives a lot of theory which happens in this particular subject. And this theory is basically possible because you have a remarkable theory, which is the general theory of relativity, which can be applied to coalescing compact binaries made up of black holes or neutron stars. And this theory underlies the efficient and sophisticated data analysis infrastructure, which is today possible because we have computing, which was not available even probably 50 years before. And using all this, as I explained to you, we can construct template banks to detect gravitational waves. We can use Bayesian methods to send out alerts to electromagnetic astronomers. And this is what allows us to do multi-messenger astronomy. We can characterize the source by using Bayesian parameter estimation techniques, both online and offline. And this eventually allows us to investigate astrophysics, cosmology, and eventually test gravity itself. So this essentially, ends the first part of my primer, which underlies everything which I'm going to tell you in the second part. So as I told Amit, this is a good point to really take some questions. So if somebody wants questions based on what I have said up till now, let's take a few questions and then we'll go on to the discovery itself. Amit, I'll leave it to you.
Yeah, so this is for the participants. So if you have any questions till now, you can use the raise hand button so that we can take your questions. Yeah, so any question from the participants? So we can take a couple of questions maybe.
Amit, I cannot see the raised hands. Can you take it? If there are questions, can you take care of it?
Yeah, so okay, I got one question. So it says, any recent success in detection?
Yeah, that's what I'm going to come to in the next part.
I think that's the next part.
So it's a good question which you have asked. So we'll come to that very quickly now.
Okay, any further question from? Okay, Subham Pandey. Can you unmute yourself and ask the question?
Yes, sir. Can you hear me?
Yes.
Yeah, I can hear you.
Yeah. So you mentioned in one of your slides, I think it was slide number 15 or something, that you use coincidence technique to eject like noise from the environment, right? But since two detectors are located like 15 or something milliseconds away from each other, then how do you make sure that you don't miss any signal when it comes?
So as I said, at this particular point, as you will see, what we really, at every particular site, you have the gravity wave data, the gravity wave channel. And as I said, there are many, many other environmental monitors. So the first thing we say is that if this particular signal is there, does it have correlation with any one of these noise channels? So that takes care of the noise at one particular detector. Now, if you are looking at an astrophysical signal, then the waveform as seen by one site and the other site should look very similar. And the signal should come, within the light travel time from each of these particular detectors. So at this particular point, we are in a situation that we don't have as many, many signals that there is any possibility of confusion, as I will show you when I show you the results. So maybe we can come back to this good question again, after I show you the results of the LIGO and Virgo observation.
Sure, thank you.
Any further questions? If not, I can't see any raise hand. Subham, you maybe close your raise hand option now. And yeah, maybe we can now proceed for the second part.
You. Okay, so now we go to the next part. So what I have to emphasize again is, as I said in my abstract, the discovery was really possible because it was a very large collaborative effort. So at some particular point, people in the funding agencies and so on essentially realized that the work involved was so much that it could not be done by a small lab just by itself. And therefore, setting up of a collaboration like in the high energy physics for the gravity wave was a very important step which happened a few years after the project was sort of funded. So what I'm going to talk about is work which belongs to the LIGO and the Virgo scientific collaboration. And it's important to acknowledge the funding sources. So this material is based on work supported by the NSF's LIGO laboratory, which is a major facility fully funded by the National Science Foundation. So now, what is the discovery? The discovery is the story about the first direct detection of gravitational waves. This happened during the first observing run, which started on September 12, 2015, and was supposed to happen to go on for about 4 months. The detector was just switched on, and immediately on September 14, the two LIGO observatories detected a coincident gravitational wave signals. The signals arrived at the two detectors within 7 milliseconds, and it was a very strong signal. It had what we call as compared to the noise, the signal was, signal to noise ratio was 24. And that is what is basically shown as our discovery picture, the iconic picture, which basically shows that at the LIGO Hanford and the LIGO Livingston. So what is shown here are the traces, the frequency time trace. So you can see here the noise of the detector, and there's a very small signal which you see here, and a signal which looks very similar to this in the other detector. So now you have to look at it more carefully. Is it because of some noise, or is it because of some astrophysical source? So what we do is the following. This is the observed data which you really see. And as I said, there's a 7 millisecond lag. So you shift one relative to the other with the right sign, and then you should be able to see that those signals are sort of very similar. Then, as I said, we use our theory knowledge. Because of the fact that we can do Bayesian parameter estimation, we can calculate what is the most probable parameters of this particular signal. So using those parameters, we solve Einstein's equations by numerical relativity and predict what the expected signal should be. And that is what is shown at the next, the second set of things. And then when you subtract one from the other, what should remain should be only consistent with the noise of the particular detector. So this is exactly the kind of exercise which you really have to do. And if you followed my first part, you will understand why that is sort of possible, because we have the theory, we have the data analysis infrastructure to do all this. So once you do that, we can estimate the parameters of our particular source. We can say that the parameter, the first mass is so much, the second mass is so much, what is the final mass? And of course, you see that there are 3 solar mass worth of, mass, which is converted to gravitational waves. So it's a very, very loud kind of signal. There is something called the black hole spin, which you can calculate out. For a fully maximally spinning black hole, this parameter would be equal to 1. So it's a rapidly spinning kind of remnant. We can also know how far it is. And then by using standard cosmology, we can calculate what the Z is. So you can see here that the full details of this particular source can be calculated. And as I said, all these numbers are statistical numbers. They are 90% confidence limits, that most likely with 90% confidence, these are the parameters of this particular source. So once we know that, we basically sort of realize that with the first detection, we already have started doing astrophysics. So what are the astrophysical implications? The first discovery of gravitational waves, the first detection of a binary black hole. People had conjectured that just as there are binary neutron stars, there should be binary black holes. And this binary black hole, if it exists, should merge within the age of the universe. And that's exactly what we are seeing. Now, if you look at the mass of this particular black hole, It is larger than 25 solar masses. Black holes were looked at by X-ray observations. Those masses were always much smaller than this. So in a sense, we are looking at a new population of black holes. So then we have to ask the question, what is the astrophysical scenario to create these particular black holes? So immediately it tells you that if you really want to make such a large black hole, you should have very weak winds. And if you want to have weak winds, there's an astrophysical property called the metallicity of this particular medium. So it tells you something about the metallicity of the medium when this black hole basically formed. So it should be correspond to a low metallicity situation. And then, as I told you, since we know this particular waveform, we can ask the question, how consistent is this waveform with the prediction of general theory of relativity? So you can test the general theory of relativity in a regime where the gravity is dynamic and gravity is very, very strong compared to the gravity in the solar system. So you can see here, it is not only about the detection of gravitational waves, it is about the start of a new astrophysics by using a new kind of wavelength. And as you said, as I said, gravitational waves are coming from a binary system, which are at a cosmological distance. So it's really amazing that we can say something so precise, because the gravitational waves were emitted 1.3 billion years ago. And at that particular time on the Earth, a single cell was transforming into a multicellular form of life. Forget about the existence of human beings. Life was just beginning its journey. And this discovery paper, which came out on 11th February 2016, had 37 authors from Indian institutions and citations to seminal papers, including Indian researchers. So it was a very, very exciting time for all the people involved in this particular subject. So in a sense, all of us are very fortunate, because February 11, on the day on which this announcement was made, was exactly like the 1919 November 7, when Einstein really captured the imagination of all the newspapers all around the world. So on February 12th, all newspapers around the world had a headline which was scientific. The cartoons related to this particular discovery, including our very famous Amun. And therefore, I am sure that if Einstein was sort of in his grave, we'd be very, very happy, because at the centenary of the general theory of relativity, and 100 years after he predicted the gravitational waves, something remarkable really happened. And all of us in our generation are part of this particular story. So we should be very, very happy that this happened during our times. For us locally, this was a very important event, because 1 week after the discovery was announced, the in-principle approval of LIGO India happened on February 17. The LIGO India proposal was made in 2011, and it was under consideration by the funding agencies for the last 5 years. No decision was really made. And the proposal was really made by the Indigo Consortium, which was formed in 2009. And as Amit mentioned, this consortium essentially was formed because we realized that this was the right time to really get into this particular game. There is already work on theoretical work in India at the Raman Research Institute in my group, and under Sanjeev Durandar at Ayuka on gravity wave data analysis. But we really wanted to be part of an experimental effort, and therefore we decided to really start this Indigo Consortium. And the LIGO India, as is supposed to eventually take scientific readings by 2026 or 2027. Why is the LIGO India very, very important? The story is because of the fact which I explained to you, that a network is really required if you really want to do astronomy. The fact is that if you really looked at the localization of sources in the sky, only using the LIGO and Virgo network, the localization is good in this part of the sky, but in this particular part of the sky, the localization is not good. On the other hand, if you really had a detector in India, these localizations also become very good. So inclusion of LIGO India would improve the angular resolution on an average by 4 times, and in some directions by a factor of 10 to 20. So this essentially is why the global community is interested in the LIGO India project, because the LIGO India detector is far away and a little more south compared to the other 2 detectors. this really is sort of possible. For the discovery of the gravitational waves on October in 2017, Barry Barish, Kip Thorne, and Rainer Weiss were given the Nobel Prize. The Nobel Prize was for decisive contributions to the LIGO detector and for the observation of gravitational waves. Half the prize was for Ray Weiss, who headed the experimental activity, half to Thorne, who was more responsible for the theoretical kind of activity, and Barry Barish, who really made the LIGO project into a collaborative kind of effort. So this really was an interesting event, a Nobel Prize which really came immediately after the announcement in a year's time. The second observing run of LIGO and Virgo started on November 30, 2016. And toward the end of this particular second observing run of LIGO, the Virgo detector joined. So remember, the first discovery was made only by the LIGO observatory. The second observing run, the Virgo also joined. And again, almost a week after it basically joined, there was a triple detection of a binary black hole. So immediately you can see the advantage that if only the LIGO detectors were operational, the sky localization was about 1,000 square degrees. Whereas the moment you had a Virgo detector, which is not really very sensitive, the sky localization becomes much, much smaller. So if you really want to follow it up by electromagnetic means, you are more likely to be able to do that. And the moment you had more detectors, you can test for things like gravity wave polarizations, etc. And that was really done by the collaboration. So immediately, as soon as the Virgo joined, we realized that our sky localization was very better. But 3 days after that, something remarkable basically happened. And that was what we call as the discovery of gravitational waves from a binary neutron star. This launched the multi-messenger astronomy, and that is what is really shown here. That on 17th, what really happened was that one saw a signal which really ramped up in frequency. There were 4,200 cycles in this particular bandwidth, and this was detected by match filter using that formula which I basically showed you, that complicated formula with those complicated coefficients. The signal lasted not for a small time, but for about 100 seconds. And it was a very, very strong sort of signal. But that was not what was exciting. What was exciting is what happened with the gamma ray detector. So what is shown here is that there is a signal, a gravity wave signal. The gamma ray signal is seeing something, and immediately a little after the gravity wave signal was sort of located, gamma ray signal was really also sort of seen. Now, once you see something like this in the whole universe, it could just be a random coincidence. So you really have to make sure that there is really the physical coincidence between this gamma ray burst and this gravity wave signal. And for that, the sky localization is very, very important. So you can see here. And for that, as I said, the fact that you can do sky localizations is very, very important. So as you see in this particular picture, as long as there was only the LIGO detectors, the sky localization was very, very large. But the moment you had the Virgo detector, the sky localization for the first triple black hole is so small, and for the binary neutron star, it is also sort of small. So we had MOUs with our electromagnetic astronomers, MOUs with them. And so we told them, if you really have a facility which can look at this particular region in the sky, please look at it and see whether there is any other electromagnetic radiation coming from this particular region. And that was really done. 10 hours later, a telescope in Chile spotted an optical counterpart to this particular signal. And once the first observatory saw it, some 5 other observatories also saw that particular signal. And then immediately we realized that this signal was could be treated for multi-messenger astronomy, and therefore 70 observatories and more than 100 instruments really focus their observational runs to this particular part of the sky, including 3 Indian facilities: the Astrosat in X-ray, the GMRT in radio, and the Himalayan Chandra telescope in optical. So all these instruments tried to see whether there was a electromagnetic radiation from this particular part in the sky. And what is really shown here is that there are radiations from different wavebands. The X-ray came after 9 days, the radio radiation comes after 16 days, and these timescales are basically determined by the interaction of the radiation with the circumstellar environment and so on. So the important point is that you have a gravity wave signal. The gravity wave signal allows you to localize the region in the sky, and then astronomical facilities can look whether there are electromagnetic radiation, and that essentially is what we call multi-messenger astronomy. So this is paper which basically talked about the multi-messenger observation of a binary neutron star merger at 3,500 authors, 950 institutes, 48 follow-up groups, 70 observatories, and about 100 instruments. And as one of our colleagues said, this was the most ambitious and emotionally charged electromagnetic campaign in history, probably for any short-lived event. So I like to sort of describe it that, people who see movies, if you looked at the first discovery was like the transition from the silent movie era to talkies. But the binary neutron star was like the advent of IMAX, because you can see it in very many different wavebands. By now, you should become experts that once you have a gravity wave event, you can calculate the parameters of this particular event. And depending on your assumption of whether the object is very small, slowly spinning or arbitrarily spinning, the parameters can have slightly different values. But what is shown here are the most likely parameters associated with this particular parameter, with this particular binary neutron star. Can you say something about the equation of state of neutron stars by using this particular observation? The answer is yes. We could say something about how much is the tidal deformability of this particular event. And from the tidal deformability, we could say something about the equation of state which this particular neutron star should be most likely obeying. So whatever I promised you in the primer essentially happened with the first discovery itself, and that is really remarkable. So there are many firsts which really came from this particular discovery. It was the first observation of gravitational waves from a neutron star system, the first observation of gravitational waves and electromagnetic waves from the same source. So many years before, people had hypothesized that gravity wave short gamma ray bursts result because of the merger of two neutron stars. So this observation supports that particular hypothesis. And there is also an associated process called the kilonova, which is powered by the radioactive decay of what are called as R process nuclei, which are synthesized by this particular ejector. So we saw the kilonova also in this particular case. So you can see here that astronomy, which was sort of conjectured, really happened with the first discovery itself. It is really amazing that, we use gold, platinum, silver on the earth, but the origin of it in the universe is an open question. People had, for example, hypothesized that maybe supernova are the sources of these heavy kind of elements. What basically has been sort of shown is that the neutron star merger is a more interesting site, because one can show that in an event like the binary neutron star merger, 50 Earth mass heavy silver, 100 Earth mass gold, and 500 Earth mass platinum can be synthesized. So the important point is that there is a very important astrophysical question which is being answered by this particular. So this hypothesis will be investigated more and more in detail. So in a sense, you sort of realize that this event is a remarkable event. And a good sign of it is that there are about 700 papers on this particular event, which try to analyze the observation, interpret the observation, create models for this particular observation, and so on. So this, in a sense, is a remarkable launch of multi-messenger astronomy, and that is really amazing. You can do cosmology by using this particular source. That is, you can measure the Hubble constant by using a source like this, because by using the gravity wave observation, you can determine the distance. By using electromagnetic observation, you can measure the redshift, and by taking the ratio of these things, you can calculate the Hubble's constant. So the binary neutron star provides you an independent way of determining the Hubble's constant. And as you know, there is a tension between the CMB and the supernova way of determining the Hubble's constant. Maybe in the future, gravity wave observations will throw light on this particular controversy. As I told you, once you have the waveform and you have such a nice observation, you can try to test the correctness of general theory of relativity. So we did such a test. For example, since you look at electromagnetic observations and gravitational waves, and they're coming within a certain time interval, you can say something about the speed of gravity and the speed of light. You can test, for example, the equivalence principle. You can test the violation of Lorentz invariance and so on. Are dipole radiation possible? What is the limit on that? The coefficients which are there in that particular formula, how much are they consistent with the data? All those things really can be sort of looked at. So we wrote a paper where we try to show the correctness of general theory of relativity by using this neutron star observation. So you can see here that this discovery of gravitational waves from this binary neutron star very immediately sort of gave us multi-messenger astronomy and the possibility to test Einstein's general theory of relativity. What is shown here is the kind of picture which we had about neutron stars and black holes before the gravity wave observations. For example, what is shown here are the masses of the electromagnetic black holes and the electromagnetically observed, that means pulsar observations of neutron stars. That is shown in this particular slide. The moment we made observations from the first and second observational run, our black holes were seen, which were more massive. The black holes were roughly of equal masses. And then we had a binary neutron star, which was here, which was different from the binary neutron star which we had seen before. So you can see here that looks like we probably are seeing a new population of black holes and neutron stars, and that is really amazing. Using gravitational waves from binary black holes, we can test general theory of relativity by different kinds of observations, by different kinds of methods. And that also has been really done by, so for example, I mentioned that there is a prediction of quasi-normal modes from black holes. We could show the consistency of general theory of relativity's prediction of quasi-normal modes with the data, and so on and so on. So we can test Einstein's theory by using black holes and by using binary neutron stars. So it is really remarkable. I don't think it has ever happened in history that when the name was given for LIGO, it was an acronym for Laser Interferometer Gravitational Wave Observatory. Many astronomers were a little dismissive of this particular name because they said that you have not even detected gravitational waves and you are claiming that you will be able to do astronomy by using gravitational wave observations. So you can see here that with the first discovery of gravitational waves from a binary black hole and from a binary neutron star, so much astronomy and astrophysics and cosmology could be done, which cannot be done by electromagnetic astronomy. We have discovered a new class of objects. For example, in the first observational run, we came up with 3 binary black holes. With the second observational run, we came up with 7 binary black holes and 1 binary neutron star. So in a sense, the advanced LIGO and Virgo their observations have been transformative. And we produced our first catalog of gravitational wave observations, which contained 10 black holes and 1 binary neutron stars. After we do our analysis, the data is released for public, and using the openly released data, the Princeton group could discover 8 more black holes in our analysis. So you can see here that in a sense, we have really launched what we can say today as gravitational wave astronomy. So with that, I end the second part of my lecture, and I go to the third part, which is talk about where we are today. So the third observational run started on 1st April and went on till the 30th September. Then we closed down for a month, improve our detectors, and start the second run, which is called O3B. This was supposed to go on till April 30th, but because of the COVID, the laboratories had to be closed on March 27th. We did something very, very remarkable in the third observing run. We sent out what we call as open public alerts. So what was supposed to happen was that toward the end of 2019, a detector in Japan called Kagra was supposed to join LIGO and Virgo. What we did during the third observation run is send out 80 alerts. That means the moment we suspect that we are seeing an important event, we send out an alert so that our electromagnetic astronomer friends can look for gravitation, for electromagnetic radiation from that particular region in the sky. 24 of them had to be retracted because they were due to the noise in the detector or because of some other problem which we discovered later. You have to keep in mind that the moment we send out a candidate, when we finish our analysis, it may not be a candidate in our catalog. And if you're interested, in knowing what happens when we do our observation, just Google the words GraceDB public, GCN circulars, or GWOSC, Gravity Wave Open Science Center. If you Google these particular words, it will lead you to infrastructure which will allow you to see online, when things are happening, what is really happening with the gravity wave observation. So what is shown on this particular slide is the amount of events which we discovered. In the first discovery, as I said, by the second discovery, we had about 11 events. But by the time we went and finished our third observing run, we could send out 80 alerts. We retracted 24. So the balance were really the events which could likely be events which appeared in our catalog. And as you can really see, why is this number increasing? The number is increasing because our detector has become more sensitive. If the detector is more sensitive, it can see further. If it can see further, it can see more volume. And if it can see more volume, it can see more number of sources. And that exactly is what we really saw. What is meant by open public alert? What it means is that the moment we suspect we see something, within about a minute, we try to gauge whether it is a noise or it could be a potential event. We localize it by using our algorithms and then tell our astronomy friends that probably there is a candidate which may be there. Then we do more careful work. It takes about an hour or a few hours. And then we either improve upon the original information or retract it. More careful again work which involves more detailed parameter estimation. That work can take about a few days or about a week or sometimes even more. And then further alert is basically sent out. So this is what is called as open public alerts, warning our astronomy friends that there could be a candidate which may be interesting for astronomy. When we analyze this particular data, we look at what we call exceptional events, and we tell the physics community and the astronomy community about it much earlier. We don't wait for doing the full analysis. So the first exceptional event which we discovered was what we call 19425. That is on April, 25th April of 2019. This was a suspected second binary neutron star. Now, why is it exceptional? Because it is heavier than the neutron stars which have been seen up till now. Its mass seemed more. Its distance was not as close by as the binary neutron star which we saw first. Because it could be seen only by 2 detectors, the sky localization is not very good. Therefore, we could not find any electromagnetic counterpart from this. Looking at the masses, essentially, we can say something that maybe it is formed differently from the other galactic binaries, and maybe there are other kinds of binary neutron stars which are not seen by electromagnetic observations. It is because of these unusual features that we call it an exceptional kind of event. The other exceptional event was something which we saw on 12th April. It was an asymmetric binary neutron star. This was seen by the 3 detectors. Unlike the detections we had seen in the first 2 observational runs, the masses were very, very different. So that's why we call it as asymmetric binary black hole. The mass ratio is roughly 1:3. And why is this interesting? It turns out that if you had a symmetric system, it radiates in the quadrupole radiation only. But if you have an asymmetric system, other harmonics of the gravitational waves can be basically seen. And also, because of the fact that you can see the other harmonics, you can measure the distance and the inclination much better. Again, in the black hole case, you don't see electromagnetic counterparts, but we definitely know that there is, in addition to the quadrupole mode, a mode which has value at equal to 3. So you can see here that again we are seeing something which we had not seen in the first 2 observing runs. The third exceptional event was again a binary black hole, just even more asymmetric. Here the masses were about 2.2 in between 2 and 3 and between 22 and 24. Because it is more asymmetric, the higher harmonics are seen even more distinctly. The distance, because it's seen in the 3 detectors, is much more well determined. The sky localization is much better. So we say that this is a dark siren. We can use it to do cosmology even better. And the fundamental question which raises is, this lighter object, is it a heaviest neutron star or is it the lightest black hole? And therefore, this kind of system is a unusual kind of system. Maybe it is formed in a very different environment than the earlier kind of systems. And people speculate that maybe if you look at young dense star clusters or disks around AGNs, these are the likely environments in which systems like this may probably be formed. So you can see here, it is not only about gravity wave detection, it is about detailed astrophysics, about population of black holes, populations of neutron stars, and the environments and the formation channels of these particular objects, and what kind of cosmology you can do with them. The last exceptional event was even more interesting because it was an event which was a new kind of black hole, an intermediate mass black hole. Black holes in general are of 2 different kinds. Black holes in the stellar mass range and black holes which are called supermassive black holes. That means which are more than 1 million solar masses long, heavy. This is somewhere in between, and this event was again interesting because it was seen by the 3 detectors. It was a very short event. There is only 4 cycles. The 4 cycles were around 60 hertz. And if you looked at the mass of the individual black holes, people believed that black holes in this mass range could not really form because the general understanding was that there is a process called pulsational pair instability, which does not allow black holes to form in this particular mass range. So it looks like we have been able to find objects in this particular mass range. So either our theory is incomplete or there are other channels by which such objects can be basically formed. And the remnant is 142 solar masses, and that is really the intermediate mass black hole which I'm sort of talking about. Intermediate mass black holes have been speculated to exist by electromagnetic or X-ray observations, but looks like we have seen something more definitive than before.
Professor, sorry to intervene.
Yeah.
So you told me to remind you. So maybe.
Yeah. So I just
4 more
in a
minutes.
few minutes. Yeah.
Yeah. Sure. Okay. Thanks. Yeah.
So the third observational run essentially gave us 39 gravitational wave events. So in addition to what we have seen up to here, we have really seen a very large population of black holes. Black holes come so often in gravitational wave detectors that now we find them to be boring. So in a sense, you have to really keep in mind that this is a remarkable discovery, and probably one of the reasons why the black hole, the Nobel Prize was given last year to Roger Penrose and to Genzel and Ghez. The fact that black holes have become ubiquitous, black hole binaries are being seen by LIGO and Virgo at such a regular rate essentially tells us that black holes are robust formulation, predictions of the general theory of relativity. So in a sense, you can see here that this Nobel Prize also has been, in a sense, affected by the discoveries made by LIGO. You may ask the question, do I see gravitational waves only from black holes and neutron stars? No. You can have gravitational waves from supernova. We look for them. We have not seen any yet. Spinning neutron stars can put out gravitational waves like the Crab pulsar and so on. We look for gravitational waves from them. We have not yet discovered them. And of course, everybody would like to know, is there a stochastic background? For example, is there a gravitational wave from the Big Bang? Is there a gravitational wave because of the stochastic gravitational wave background from a superposition of all these sources? The LIGO and Virgo collaborations look for gravitational waves from all these kinds of things, but there is no definitive discovery, and therefore I have not talked about it. I just want to end by pointing out that the participation in all this goes by through the LIGO India scientific collaboration, whose PI currently is Sukant at IUCAA, and I am a co-PI. These are the 14 institutions. There are about 99 members. And if you really look at the activities which happen at these various places, which are sort of mentored by these various PIs, you will see that in many analyses which are done by the collaboration in the burst sources, CBC, stochastic, continuous waves, characterization of the detector, there is a presence of Indian groups in these particular activities. I just flash this list so that students who are interested in this particular activity really can contact the PIs at these various places and do an internship during summer so that they can decide whether they would like to contribute to this area, emerging area of research. Since it's an interest, it's an engineering audience also, I just wanted to point out, as I mentioned in my earlier presentation, that this is an area where there is equal participation from physicists, experimenters, theorists, models, data analysis people who do machine learning, etc., and a lot of technology of different kind of regimes. So in a sense, the LIGO India project interfaces and calls for engineers who must be in your institutions. So please learn, please sort of keep in mind that there is an opportunity out here because there is a facility which will challenge experiment and technology at the frontier in this particular area. If you want to learn more about what LIGO does, please look up what is called as the LIGO Science Program. Every year we put out a particular document where we say this is the kind of analysis we will do in the coming year and over the next few years. And if you can participate in those particular activities, you can become a member of the LIGO Scientific Collaboration and do that. What we practically advise is that please get in touch with the various groups which are there in India, and through them, try to learn more concretely what is involved and then go ahead with that. Amit, I essentially have now a few slides on where the future is going. If I run out of time, I can stop here. Otherwise, I can just go ahead for the next 10 minutes.
Depends. Yeah, maybe just 2-3 minutes. Is it possible?
Yeah, I just try to give an idea. So as I said, O3 is not the end. We will now go on to the next run, which is called O4, which is supposed to run for 1 year. And as I told you, the Kagra detector is supposed to come online. And based on what we have discovered up till now, we expect to see in the fourth run, about 8 binary neutron stars, 2 neutron star black holes, 68 binary black holes, and so on. And as I told you, the important thing is that the sky localization, which is small, will become even better because we have a detector now in Japan. And that is going to allow us to do more astronomy. And that is really the interesting point. When will the fourth observing run begin? The earliest it will begin is in June 2022, and then it will last for about a year. Much has been affected because of this COVID pandemic, and therefore we are also facing all that. So what will happen eventually? As I said, in the next decade, there will be detectors, as I said, including a detector in LIGO, India. And when LIGO India comes online in 2026, it will be like the best LIGO detector in the US. It will be in what is called as the A+. It will be able to see further in the universe like the LIGO detectors. And if you really look at the Virgo detectors and the Kagra detectors, they cannot see as far because they are not sensitive enough. So this is really the amazing challenge. If LIGO India comes online in 2026, it will be one of the best detectors in the world, like the LIGO detectors, and that is really what is really amazing for opportunity. Does the end of LIGO, bring the end of this particular field? The answer is no. Already the community has started looking at what are called as beyond the advanced LIGO. That is what is called A+. Then the further next generation detectors are called Voyager, Einstein Telescope, Cosmic Explorer. And there is a space detector which is called LISA, which is supposed to come online by 2034. So the third generation science drivers pushes gravity to its extreme, looks at matter in its extreme form, and would allow us to do cosmology by exploring the universe in the large amount. The third generation detectors are supposed to be 10 times more sensitive. So obviously they will converge at 1,000 times more volume, and therefore the number of sources they will look at would be even more. So what we really expect to happen is that by the time the third generation detectors reach their design sensitivity, they will be able to see the neutron stars and neutron stars up to the Z of 10, or black hole. So essentially all the neutron stars, binary neutron stars which exist in the universe, or all the binary black holes which are massive, we will be able to see with the third generation detectors. And as I said, these are not sources which electromagnetic astronomy could ever have shown you. I want to sort of emphasize my last two slides by basically telling you that just as electromagnetic astronomy is not just optical astronomy, it goes from optical to radio to X-ray to gamma ray and so on and so on. Gravitational waves also span 2 decades in frequency. For example, the ground-based detectors are at about kilohertz, but then if you look at gravitational waves from the Big Bang, they would be in the attohertz frequency range. So you can see here that eventually, by different means, the pulsar timing arrays look for gravitational waves from supermassive black hole binaries. Gravitational waves from the Big Bang will be looked at by detectors called the Big Bang Observatory and so on. And once you can detect gravitational waves by 2 different wave bands, you can do what is called as multi-band gravitational wave astronomy. For example, I will be able to see a detector, a source in LISA almost a year before it is seen in LIGO. So I can be prepared to do my sky localization with my astronomy friends, and that is a big exciting field which will open up over the next decade. And what are the kind of sources which you look at? As I told you, there are all these kinds of sources. There are all these kinds of ways by which we look at them. So from sources which were known knowns and known unknowns, eventually we hope to see sources which we didn't know. Unknown unknowns are what we are looking for eventually. So with that, I come to my concluding remark. Black hole astronomy was ushered in by the first black hole discovery, detection, and multi-messenger astronomy by the neutron star discovery. And what was the game changer? The game changer was the LIGO and Virgo network and their ability to localize the gravitational wave source to a small enough region so that we can send alerts to facilitate EM follow-up. And in the future, as I said, next year, the Kagra detector will come online. And in a few years' time, LIGO India will also join the global network. With the third observation run, already insights into astrophysics, cosmology, and fundamental physics, which were assessed feasible, have been consolidated. And as I said, we basically have been able to extract out a lot of astrophysics, cosmology, and gravity related tests by using these binary black holes and binary neutron stars. So in a sense, what you are hearing or what you are sort of picking up are faint strains of the gravitational wave symphony in which the universe is sort of drowned. In a sense, these are like the whispers of a new astronomy. And what is interesting is the fact that when you make your detectors more and more sensitive, you really will need to know your theory even more accurately. And what has happened over the last couple of years is that new interfaces of general relativity and quantum field theory has sort of really emerged. The kind of techniques you can use in field theory to calculate higher order corrections are being adapted to do the calculations for gravitational wave templates. So I would entreat the younger colleagues in the audience that please come and decipher the universe by using gravitational wave observations. Multi-messenger astronomy is really sort of taken off. It is the first light of multi-messenger astronomy. And there are many, each of these blobs are events to be sort of discovered. We are waiting to look for gravitational waves from a neutron star black hole system, from a supernova, from a pulsar, from the stochastic gravitational wave background. And what is sort of indicated in pink are activities in which citizen science is sort of possible. And therefore, I would encourage amateurs also to basically join in this particular effort. Every particular thing here is something waiting to be sort of done. So there is a lot of promise in this emerging area, like you heard in the other two talks. So there is a lot to be done, and this is not the end, but just the beginning of something which is really willing to happen. So with this, I just leave this last two slides. As I said, anybody who's interested can look at the website of GWIC, which is the Gravitational Wave International Community. It basically will tell you globally what is happening. And there is a LIGO India website, which will tell you what are the opportunities related to LIGO India, which is available to students and engineers. And as I said, there are citizen science efforts possible. For example, as I told you, there are many noise sources in the LIGO data, and we really need people, citizens, to look at those noise sources and help us classify those noise sources. This is a facility which is called Gravity Wave Spy. There is another citizen science thing called Einstein at Home, which integrates all the computers which are idle in the world to do gravity wave data analysis. And so if you have a PC which is lying idle in your home, you can sign up by bringing this Einstein at Home on your laptop. So many opportunities. So the most important thing is to stay safe during these troubled times and just look forward to a new dawn which is going to sort of emerge. So again, thank you all for joining in this particular talk. I appreciate you joining in these troubled times. Thank you very much.
Thank you, Professor Iyer, for this excellent talk on this topic. I hope there will be questions now from the students. So if you have any question, you can use the raise hand button so that we can take a few questions now. Or you can also type your question. Both are fine. Anyone?
When I see dead silence, it either means I have been great or I have sort of gone full toss.
I don't think, maybe it's late also, too late. Anyway, yeah, so I do not see any, but maybe you said that you might answer the question, but that's already maybe answered. There was a question at the very beginning from Vivek that any recent success in detection, but
So as I said,
second part is entirely on this, I guess.
Exactly, yeah. So basically, as I said, we have made discoveries. The second catalog essentially gives you all the black hole events which we have sort of seen and the neutron. So the discovery of gravitational waves from binary black holes, binary neutron star kind of systems is ubiquitous. As I said, every time we turn on the detector, we see them. And therefore now there is a population of sources which we have seen, and therefore the astrophysical challenge is to model this population and try to find out what is the astrophysical channels by which these objects can be formed and so on. So like we have population of quasars, population of pulsars, population of active galactic nuclei, etc. We have a population of gravity wave sources, and we really have to play the game of how many are there. Is there a what is the pattern in their masses and spins which we see, and what is the astrophysical channel which is consistent with these kind of observations which we are making. That is a very active game which is happening right now.
Yeah. Any further question? I don't see any raise hands option. Okay, there could be a question. Yes. From Aleka is a question. Wait a minute. How do we know whether gravity wave signal is from NS neutron star merger or black hole merger?
Okay, that's a very excellent question. I didn't really go into the detail. So if you remember, I showed you, two diagrams after I showed you that complicated formula. One for the waveform from two black holes, which black holes are very, very rigid. So the point particle approximation, that they are almost like point particles, that approximation holds for a sizable amount of time. But if you have two neutron stars, then it's made from new matter, and matter deforms. When the two neutron stars come close to each other, one neutron star tidally deforms the other. And once there's a tidal deformation, the waveform, in the waveform, this tidal deformation is sort of coded. So the deviation of the waveform from the point particle limit is gives us a measure of the tidal deformation, and that essentially helps us distinguish the neutron star case from the black hole case. If you cannot measure the tidal deformation, then the only criteria we use is that there is a limit to the maximum mass of a neutron star. For example, we believe that neutron stars cannot be more massive than 3 solar masses. So then there is the only criteria we have is the masses of the object. But then it becomes tricky. So when you can't measure the tidal deformability, the classification becomes a little more tricky than if you can measure it.
Any further question from anyone? You can still use the raise hand option. I do not see any. Okay, then maybe it's time to say thanks to everyone from my side. So first of all, I would like to thank Professor V.S. Rao, our VC sir, and Professor D. Narayana Rao, Pro-VC sir, and Professor Durga Rao, Associate Dean, our head of the department, Professor Ranjit Thapa, and also to all the invited speakers, Professor Rohini Godbole, Professor Vasudev Dasgupta, and Professor Balayar for these wonderful talks. I would also like to thank all the participants because, as we are already saying, that this is a difficult time. So you have managed to join the meeting. That is very good. A thank to the ITKM, the department who has taken care of all those live streaming and assigning this Zoom meeting. Thank you so much for them. And for the students, couple of things that if you want to have a participation certificate, e-certificate that we can issue, so please let us know. And we also plan from our department that we will going to organize such events, maybe one-day events or 2 days event or symposium workshops regularly. So keep in touch. Maybe you can like our channel, maybe in YouTube to get updated. So is there any question? Okay, so thanks from the participants as well. So I must say thanks to all of you. I would close the meeting, but before that, please take care of yourself. This is we are going through a very difficult time. Stay at home, stay safe, and goodbye from my side. Maybe we will see next time.
Yeah, thank you all. Take care. Thanks, Amit.